Hi grade 12s, welcome to my channel. Let us discuss this paper, which was a preparatory examination paper written in Gauteng during the prelims of 2025. So this is physics paper 1. There seems to be an outcry from students about this paper. So out of curiosity, I figured let's just have a look at it and see what is in it. Otherwise, folks, I need to thank you all for supporting my channel. Yes, it's growing very slowly, but ever surely. So I'm really humbled by that. And please continue to do that support. I will do my best as well to give you the best of my ability in ensuring that you get some good results out of your attempt in physics and maths. All right. Let's have a look at the instructions. It's very important to read these carefully, guys, but of course we need to commit these to memory because they have a direct impact on how we score maximum marks in different questions. Okay, so the rounding off here is 2 decimal places or more. Okay, minimum means 2 or more. And of course, when given a chance to make a choice and to perhaps describe or rather explain for the observation, we can actually use anything that is applicable. So we need to keep that in mind. So let's get to these questions. So question 1 is MCQs. So let's take a walk through them and see what's going on. 1.1 reads, a mass hangs from a single vertical string attached to a ceiling. All right. So which one of the following forces is the Newton's third law pair? Okay, this is when we talk about action, reaction, coupling, or pairing for that matter. Okay, which one is the Newton's third law pair of the weight? Okay, we know that the weight is Fg of the mass. All right, so it helps again to just picture what this should look like. So if this is our ceiling and we've got our mass, say it's a ball, and it hangs like that, we know that the forces acting on this mass is going to be that of gravity, Fg, and there's going to be tension on the string. Of course, knowing that there is the mass of, the earth as well, right? And we know that the earth, the center of the earth is what is exerting the gravitational force, Fg, on the object. And now we want to know, this is the action. The gravitational force is our action. So what would be the reaction? Obviously, it's going to be the same amount of force according to Newton's third law, but it's going to be in the opposite direction. So we can say this is minus Fg. Okay. So that would be our reaction to the action by the center of gravity, the center of the earth. Of course, this is the earth. Okay, right, so let's read. The force from the ceiling acting on the mass, that describes the tension. No. The tension on the string, again, talking about the same thing, not at all. The gravitational force exerted by the mass on the earth, that describes minus Fg. That is true. The gravitational force exerted by the earth on the mass, well, that's the action, not the reaction. All right, so our answer, guys, is C. Okay, it helps again to understand this and to know it well. Right, 1.2 reads, a block is at rest. So when it is at rest, what does that mean? Initial velocity u is 0. It rests on a rough surface, so that means we've got static friction. Now, the surface is at an angle, theta, to the horizontal. Okay, you can see that. The block remains at rest. Very important. Remains at rest as theta is slowly increased. Okay, so essentially, if we can just draw, you know, what happens here in terms of forces, we know that there's going to be the gravitational force straight down, which is Fg, and there will be normal force acting perpendicular to the surface. So that's our normal force. Okay, and there's going to be the static friction acting parallel up the incline. Okay, that would be the static friction over there. But since our gravitational force is acting at an angle, we know that it splits into its components, right? So it has components that it acts through instead of acting directly. Okay, so these components have the gravitational force as the resultant force. One thing for sure is that these ones are perpendicular to each other, hence we call these the perpendicular components of weight. And of note is that the angle theta is the same as the angle always between the gravitational force and its perpendicular component. So this is Fg perpendicular, and this is Fg parallel. Okay, so this is the scenario that we have. Now, what is the story? The question is, which of the following best describes how the magnitudes of the static frictional force of the rough surface on the block and the normal force change as theta is slowly increased? Okay, now let's think about it. If we've got our surface there, right, and we've got our gravitational force straight down, right, and of course, essentially, what we will see is that these components of weight, let's just focus on the parallel component for now. There is the parallel component of weight. Perhaps we can think about it. Perpendicular component is over there. Right. Let's think about it, because we need to think about these issues. And also there is the normal force over there. Now what happens is when the surface here is becoming more vertical, I guess that's when the theta is increasing. What happens to the parallel component of weight? It has to assume also a more vertical orientation. Right. Now we can see that if that happens, this narrows down our perpendicular component. Right. It narrows it down, so to speak. Okay. As we can see, this one slowly closes in. Of course, guys, this sometimes is not so easy to demonstrate, but I think our main goal is to check our Fg parallel. When theta is increasing, it also increases. Because remember, from vectors, Fg as the resultant is going to be equal to the sum of its components, right? That's just in principle. But now we know something, that when this slope increases, we know that the parallel component of weight assumes a closer value to that of Fg, because it's becoming almost vertical, eventually becoming Fg itself. So we know that this one increases as theta increases. But what happens to the Fg perpendicular? It actually decreases, because Fg is a constant, right? That is vectors. Again, folks, one can argue and say technically this should have been Fg squared, Fg parallel squared, because that was a right-angled triangle. But now we don't really care about the technical factors. All we care about is that vectors are actually additive or summative, whatever. Right, so we can see that Fg parallel actually increases as theta is increased, but the FG perpendicular decreases. Okay, so that's what we notice. But now let's go back to this diagram. We will notice something that technically this object is not moving either down or up the incline. So it means this force FG parallel must be exactly balanced by the static frictional force. So those forces are initially equal. Second, we can appreciate that the normal force is also perfectly balanced by the the perpendicular component of the weight, because this object is not moving up, meaning being lifted off the surface, or is it dipping into the surface. So those two forces are balanced. So this is a state of balance. Okay, right. But now, from this state of balance, we can appreciate that of the forces responsible for whether this block moves parallel to the surface or not, it's going to be these two forces. So we will have our FG parallel and our static frictional force, and these two are perfectly balanced, and that's why this object is not moving down or up slope. The others don't really do any work on that object. Right, so now we've got a situation where we notice that FG parallel increases while the FG perpendicular decreases. So what would happen in this instance? This would mean with the FG perpendicular decreasing, it means our normal force will also decrease, right? Because those two are still perfectly balanced. So the normal force has to drop as well. Okay, that we understand. Now we understand that static friction is equal to the μs, its coefficient of friction, times the normal force. Now principles suggest that if our normal force decreases, our static friction should decrease. Okay, so now these changes we end up with is that we've got our FG parallel increasing, FG perpendicular decreasing, eventually the normal force decreasing. So this is suggesting that, okay, our frictional force is also decreasing. So this means our normal force is definitely taking a dive. Okay, we're not going to take the part that says it doesn't change. Now when it comes to these options, although these ones are talking something else, but they're already eliminated, so we have to deal with C and D. So what's happening here? Is it decreasing? Sounds right. Is it increasing? Well, that's what the principle is telling us. But then let's go back and say, okay, look, the scenario that is going on now is suggesting that our FG parallel has increased and our frictional force has decreased. Can you see? We can say 3 times, just 1 time. Now this creates a situation where there is a resultant force in the direction of the bigger force, and this would mean this object will start accelerating. But we were told this thing remains constant. So you see there's a bit of a problem here. So if it remains constant, this is saying, hold on, this new scenario, yes, our FG parallel has increased, but for this not to move, it means our frictional force as well must have increased. Now the question is it possible for the frictional force to increase? Well, with static friction, we can be at minimum or at maximum. Okay, so until we surpass maximum, we cannot say that it does not increase. It can increase from minimum to maximum. Now, since we were given a very bold statement that this object remains at rest despite an increment in our value for theta, which would mean FG parallel increases, but for friction to stop this object, it must have increased. So technically, the answer here is yes, it actually did increase. right? But not decrease, because if it decreased, then the object would start moving. So technically, our answer here is D, because static friction doesn't behave like kinetic friction. So we need to know it can be minimum to max. So this means in this instance, we caught our frictional force on its increment from perhaps a minimum value approaching the maximum value. So these kinds of questions, the principles when incorrectly applied can lead to disaster. Okay, so static friction needs to be treated a bit different to, the usual stuff. So that's how we get the right answer there. Of course, guys, this is a definite higher grade question. You cannot answer this blindly, because you can see there's a catching answer C, and it's certainly not the correct answer. But the correct answer here in this context is it's D. Okay, be very careful. Be very careful, guys. All right. 1.3 reads, a ball is thrown vertically upwards with speed v from the top of a building. At the same time, ball B is thrown vertically downwards with the same speed v. Okay, both balls reach the ground at the same instant. Oh well, that's questionable. Is it possible that they can reach the ground at the same time? Not at all. Well, let's think about it, guys. If we draw a position time graph, so to speak. Okay, there's our building top. We've got ball A thrown vertically upwards. It reaches maximum height, comes back to the same position. Then it goes to the ground, okay? And we were told that it's thrown at velocity v. So this is ball A. Okay, now we need to think about what is going on. We are to ignore effects of air friction. So this tells us that we are dealing with VPM, vertical projectile motion, and we know that in VPM there's only one force acting, Fg. And if this is the case, it means acceleration is g, meaning it's a constant. All right. So we've got these two balls, ball A and then there's ball B, and it's thrown vertically down. All right, so this is ball B. And of course, if that object was thrown and we're choosing up as positive, it means the velocity of B is going to be minus V. But we know that that's very same ball A, when it reaches the same height on its way down, it's going to be at the same velocity but in the opposite direction. At the maximum height, it is 0. So folks, this doesn't make sense that these two balls can reach the ground at the same time. You know why? Because this one takes a longer route. Ball A takes a longer route to get to the ground. Yes, the truth would be since they leave the same height, in essence, with the same velocity, and we know they're accelerating with the same acceleration, traversing the same height of the building, they will certainly reach a final velocity of B that should be equal to the final velocity of A. Okay, that is true. But this is not going to happen at the same time. It's impossible. Right? Think about it, guys. Let's say this is my yard. And this is my neighbor's yard. Right? There's my gate. There's my neighbor's gate. If I walk at a particular pace directly, then when I decide to walk all around with the same pace before I enter, you see, I will definitely take longer if I go around. Yes, I will be using the same velocity v. There's no way I can reach the gate at the same time. So this scenario is just wrong, okay? It just doesn't make sense. The other issue that one can consider is a velocity time graph. You see, if we do a velocity time graph, Okay, so we would have our velocity here in meters per second, then we've got time in seconds. Okay, now we know that if we chose up as positive, this object started from a positive velocity, right? And it decelerates to maximum height and then decelerates to the ground. Let's assume this is when it hits the ground. Just want to make a very nice sketch here. Say this is when this object would hit the ground. Look at this thing now. Come on, Winnerman. Right, so this is when this object would be hitting the ground, okay? Right, and we can see that the velocity for this is going to be the same. Right, now look at this. If we throw this one at the same velocity but down with the same acceleration, do you realize that that object will actually hit the ground? Now pay attention, these two need to be parallel because it's the same gradient. Remember, on a velocity versus time graph, the gradient is the acceleration, and since this is due to gravity, it has to be the same. So can you see this one would reach that velocity much earlier? Can you see that? It reaches that velocity much earlier than the other one. Say this is minus, say 20 times v, we don't know. Because this one was v, this one is basically minus v. Okay, same velocity, same acceleration. We know that this one is going to hit the same final velocity when hitting the ground much earlier than the other one, because this would have been A, this would be B. So that statement was totally misleading. Anyway, you see, when a situation like this happens, it already spoils the mood. But hey, we just have to answer the question, because at the end of the day, instructions do tell us we need to answer all questions. Not answering all questions is already a bad behavior. Okay, which of the following statements is true about the speed at which the balls hit the ground? We know that it's going to be equal. Okay, let's look for that. The speed of ball A is greater than the speed of ball B. Not possible. We were told that it's the same, just oppositely directed. The speed of ball B is greater than the speed of ball A. Again, not true. By the way, this is when they hit the ground. Sorry, I'm making a mistake now. When they hit the ground, we said that should be the same. Okay, so no. The speed of ball B is equal to the speed of ball A. Yes, that is true. I mean, we can demonstrate it with our velocity time graph even better than our position time graph. And the speed of the balls will depend on their masses. No, it is independent of mass. Why? Because we are doing acceleration due to gravity. We know that it has nothing to do with the mass of the object. Okay, it's predetermined. So the velocity changes due to the acceleration by the gravitational force, by the center of the Earth. So that means the change of velocity here is independent of the mass, so it's not possible. So our best option is C. Although the statement that says these two reach the ground the same instant is spoiling the mood here, but I guess that still is a correct answer for the question that is asked, at least. So perhaps that statement, or at least the question itself, does redeem that incorrect statement given. Okay guys, always explore things in many ways than one. In fact, when we want to talk about speed, a velocity time graph is way better than a position time graph in giving a clear opinion. Okay. 1.4 reads, two trolleys of masses 3m and 2m are connected to each other and are moving at an unknown velocity. Okay. A small explosion between them causes the trolleys to move apart in opposite directions. The trolley of mass 3m moves at velocity v, and the trolley of mass 2m moves at velocity 4v. Of course, if we choose to the right as positive, then this means this is going to be negative, that's going to be positive. Okay, this is after the collision, so we're talking momentum here. Right, which of the following statements is correct? Right, the total momentum before collision, the total kinetic energy after collision. So of course we've got enough information on the after, so let's look at it. So sum of EK after is going to be half, the mass is 3m, the velocity is minus v squared, plus half the mass is 2m, the velocity is 4v squared. So this is going to give us 3 over 2 mv squared, plus these ones take care of each other, it just becomes 16 mv squared. Now we can see there that these are like terms, so 2 by 16 is 32, plus 3, that's 35, divided by 2, that's going to be 17.5 mv squared. Okay, so this is good, this is good. Already those two options, no matter what the pair says, they are out. Okay, now the challenge is finding out the partner to this. What about momentum before? And remember, we were not given any indication that we have at least a closed system or an isolated system. Okay, for me, students gravitate towards this. This is a special case, a super special case. That is one that we should not assume unless we have proof for. Think of, when you see one of your peers absent at school, your first impression is that they are alive. I mean, they are alive where they are. You wouldn't presume they're dead. Okay, this is that kind of an analogy that I can put, that this is where the bare minimum and the safe minimum is the best to choose, because an isolated system is much more it's super selective than a closed system. And when we talk momentum, normally a closed system is enough. But if we take it a notch further, then something else also happens. So we were not given anything. So this one is easy to assume, if not given. But this one, never assume it. Okay, please. You can never assume someone is dead unless there's enough proof or indication that they might be dead. Right? Right. Now, let's assume we have a closed system. We know that the sum of momentum before is going to be the sum of momentum after. Right, we have enough information on the after. So this is going to be 3m into minus v plus 2m into 4v. This gives us minus 3mv plus 8mv. These are like terms, they simplify to 5mv. Okay, at least we have it. The 11mv, well, it's questionable. It's possible for it to be 11mv, but at this stage, we have no grounds to justify that. So in essence, we could be forcing the scenario to get to that. But once we have a known principle, which is the principle of conservation of linear momentum, we can sit home free with our option B. Okay, very easy question to answer, but it was complicated by the fact that we needed to perhaps work with an assumption, which is not fair. There should be enough indication of what system we're dealing with so that we can do the necessary determinations. 1.5 reads, a car is moving in a straight line, more of the grade 10 type of motion. The velocity of the car decreases with time. If it decreases, we call this one a deceleration. Okay? Or it's accelerating in the opposite direction. Okay, with time t as shown below. Now, folks, whenever we see a graph like this, which does not hit the origin, we need to think of an equation, because we understand that issues of direct versus indirect proportionality is only modeled, it's only modeled best by mother functions, okay, or parent functions. Now, parent functions will pass through the origin. They will have an x and the y-intercept at the origin. That is the most characteristic thing about mother functions. But in this case, we don't see a mother function. So this means we need to look for an equation, but this is linear. So it's in the order of y is equal to mx plus c. This is where m, the gradient, is less than 0. Okay? Because we can see it's a negative gradient. So we need to look for an equation that looks like this. But we know that technically velocity as a function of time is v equals u meaning the initial velocity, plus acceleration times time. And if we try to make our analogy look alive, it's going to be v is equal to at plus u. And we know that our u here is a constant, and our acceleration is also a constant. Whereas these two, t and v, are variables. Right? T being the independent and v being the dependent. And we can see that this analogy works very well. And of course, this is clear that our a here is less than 0 because it's a decreasing gradient. So this equation is the best representation of that graph. So it always helps to know this, because without this idea, there can be very dangerous deductions made. The reason why I'm going through this is that once we have an equation that is neither a mother function nor passing through the origin somewhat, we cannot talk of direct proportionality versus indirect proportionality, but rather a correlation. This offers us to correlate, or correlate, as you can call it, correlation. So we can only correlate the two variables. We cannot talk of direct proportionality versus inverse proportionality. Now, which one of the following graphs best represents the power of the braking system over this period of time, t? Okay, so if we look at these equations, these graphs, we will see that, okay, this one touches the origin, but it's parabolic. So we cannot say exponential, but this is parabolic. So this can be described by an equation y equals ax squared, where a is greater than 0, right? Knowing functions. This one would be modeled by an equation y is equal to b, where b is a value greater than 0, but any real value for that matter, right? Of course, the gradient here is 0. It's a straight line. Now here, it passes through the origin. So this can be modeled by an equation y equals ax. In fact, let's just say mx. It's a straight line. Okay? Where m is greater than 0. Here we can talk of direct proportionality versus inverse proportionality. This one, we can see it doesn't pass through the origin. It's a straight line, can be modeled by y equals mx plus c, where m is less than 0 since it carries a negative gradient. So we need to think about it now, that the best thing to do here is to express power as a function of time. Then we would know what to do here, which graph would best represent this. So we know that power is the rate at which work is done. Now we don't have somewhat power as a function of time at this stage. Okay, we can go on and say power is, we know that work is force times displacement, okay? Of course, cos theta, whatever, but at this stage we just ignore that thing. It's all about directions. So divided by time. Nicely, we can see that, okay, this friend here, when we selectively look at that, it tells us that our power is going to be the force times the velocity, isn't it? Because change of displacement over change of time gives us velocity. But again, we still don't have power as a function of time. But this guy we can express as a function of time. So we know that power is F into velocity. We saw that it's AT plus initial velocity. Then we fold things out. Power is going to be FAT plus FU. Of course, that's not an insult, guys. Great. So we can see this fits this description of y equals mx plus c, because technically these other graphs do not. The reason why I'm saying they do not, yes, this one qualifies, but the problem with that is, you see, the y-intercept is the origin, meaning there's no fu. But fu is actually there because there is a force responsible for braking, meaning for the deceleration. Newton's second law tells us that if we decelerate, we have a resultant force. 2, u is an initial velocity from which we broke this car. So technically, not broke, but we braked the car. So essentially, these two exist. It means we must have a non-zero y-intercept. So in essence, all these other graphs are actually failing. Perhaps this one might be surviving, but these ones that have a y-intercept at the origin doesn't work. And the worst part is that this is parabolic. As we can see, this is linear. Can be given by y equals mx plus c. So already that is not likely. This one is not possible because it says our y-intercept is 0. This one is likely. Perhaps b is also likely when the gradient is 0. Now we go back and find out. Technically, in this model, what does a represent? A deceleration. And we can see that this is part and parcel of our equation. So there was a deceleration. So this thing exists. And for a deceleration to be present, there must be a resultant force. So in essence, this is also falling off because it's suggesting there is no gradient, and we actually do have a gradient on our equation. So this leaves essentially D as a best option. Okay. So again, only because we could identify power as a function of time. So again, we used the concept of simultaneous equations because we took that and went and plugged it here. And it eventually gave us the result that could help us to describe power as a function of time so that we can see what type of a situation is. Now, again, to confirm if ever you are doing the right thing, you can even check what would be the gradient in this equation. So we know that m is going to be the change on y divided by the change in x. So what is power? Is force times velocity, all divided by time. Again, nicely selecting these two, because with multiplication and division we can select things that work at our convenience. So this is A. So indeed, there is our A showing up. It's FA. So obviously we are satisfied. We've got it right. So answer there is D. Of course, this is one of those questions that are not that easy to answer. Of course, students can carelessly guess here by relating velocity and power, but you see the equation did not show power as a function of velocity, but rather of time. So you will get caught if you make very careless statements. And remember, this is correlation rather than direct proportionality or inverse proportionality. So we can just say power is negatively linearly correlated to time. You can't say inversely proportional. Okay, remember that. 1.6 says a car moves at a constant velocity towards a learner who is standing, so that means the learner's velocity is 0. On the side of the road, the driver hoots as the car moves towards. See, the car is moving towards the learner. So this is the Doppler effect, right? Which of the following statements is correct? The speed of the sound heard by the learner is higher speed, and it's higher than the speed of the sound emitted by the hooter. Remember, the speed is a constant. 340. Is it 340? Yes. Meters per second. So it's never high nor low. Now the wavelength of the sound heard by the learner is higher than the wavelength of the sound emitted by the hooter. Now wavelength in relation to frequency. Remember, when we talk about sound here, we're actually examining sound quality. And we call this the pitch. And the pitch is directly proportional to the frequency of sound. Now wavelength is inversely proportional to frequency. So a longer wavelength, which in this case, this one says higher, but technically the right word is to say longer wavelength, means a lower frequency. Lower frequency means a lower pitch. But remember, when the source is moving towards a stationary listener, the listener will hear a higher frequency apparently, right? It's not actually the reality. It's sort of like a relative type of a situation. So no, the frequency of the sound heard by the learner is higher. Yes, it's going to be higher than the frequency of the sound emitted. That's truly the Doppler effect. Both the wavelength and the frequency of the sound heard by the learner are lower. No, it's not both, but it's only the wavelength that's going to be lower than the wavelength of the sound emitted by essentially the hooter. So the best here is C. Okay, please guys go through all the options carelessly and carefully because it can get very confusing. Now 1.7 reads, two small spheres, each with a net charge of minus q, exert a force of magnitude F on each other. Right, we can see this is repulsion because these are both negative charges. Right, very important to notice. Okay, one of the charges is now replaced by another with a charge of minus 4q. In the process, the distance between the objects is doubled. Okay, we knew that F initially was given by our K, Q1, Q2 divided by R squared. Now, whenever we double one of these charges, because the force is directly proportional to the product, it means we're going to quadruple the entire force, right? But R squared, when we double the distance, is going to be 2 squared R squared, which gives us 4 R squared. And so this and that, they divide to 1. So in essence, we remain with the same force, F, okay? So that's very important. So it says the force that one charge now exerts on the other charge is, again, it just remained the same. Okay, very clear and straightforward. No manga business there. 1.8 reads that a battery with an EMF E and internal resistance R is connected to a switch S and 2 identical resistors. Sometimes this word can be thrown very carelessly. Be very careful of its implication, right? It's shown in the sketch below. Each resistor has a resistance R, okay? meaning they are identical in terms of resistance. We can appreciate that now. Right, which of the following statements is correct? When switch S is closed. So obviously if we close switch S, we're going to start to have a current. Now how does the current flow? You know that the longer bar represents a positive end and the shorter bar represents the negative end. And of course the unit is a cell. Right, so this is a one cell type of a thing. Could be more of a remote controller. Of course, following the conventional current, it's going to come out this way, go all through the resistors and back. Right, once this happens, we know that there's internal resistance. It's going to cause us to lose voltage due to working charge or pushing charge against a charge gradient, I guess. It's not an actual resistor, but it's just that gradient that we have to force charge across once we get back to the battery. Okay, now the voltmeter reading is E when an ideal voltmeter is connected across the two resistors. Okay, well, we know that if we connect a voltmeter across the two, say that would be the V, it would be the same as connecting a voltmeter across the battery terminals, because that would read the total resistance, the total voltage of the external circuit. So this is one and the same thing, okay? Please be aware of this. So when we say an ideal voltmeter, we know that this is a high resistance device, okay, meaning it does not allow charge to pass through. So we are told here that when we fit a voltmeter across these two resistors, whether directly or across the terminals of the battery, this would read the EMF. Okay, that's not true, because we said we're going to lose voltage because of internal resistance. So when the current flows, this is going to chow the energy. We know that this battery will start to become hot. We lose that as heat, okay? So there will not be enough. It won't be the same as E. There will be less than E available for the external circuit. The voltmeter reading is less than E, okay? When an ideal voltmeter is connected across the battery, that sounds right, because we have lost voltage due to the internal resistance. Now C says the voltmeter reading is half E when an ideal voltmeter is connected across the two resistors. Well, we cannot say for sure because there's no clear proportionality so that we can know exactly by how much. Why? Because we know that EMF E is basically equal to the total current times the external resistance plus total current times internal resistance. And we know that these are constants when the current, of course, doesn't change. And the external resistance here is perhaps variable. So in essence, we know that this would give us what we call a correlation rather than a direct form of a relationship like inverse versus direct proportionality. So we cannot be exact as to by how much that should drop or increase. So this is already outrageous, okay? The voltmeter reading is E when an ideal voltmeter is, again, saying the same thing as A, so this is out. So basically here our best is B. Okay, again guys, it helps to understand exactly what is going on. Again, when we talk of relationships, we need to think of the equations governing matters, or at least that can display the relationship. You'll understand this when you do statistics. You will see that for a different scenario that you're researching, a certain model is the best chosen to assess the relationship between the variables, rather than to carelessly just jump in and use whatever you will. All right. 1.9 reads, Which of the energy conversions below takes place when an AC generator is in operation? We know that it's mechanical to electrical. So this one is just straightforward. Potential, no, because this is stored energy. But we prefer kinetic energy. So when we say mechanical, remember mechanical energy is basically potential energy plus kinetic energy. And this guy is now covered because we need movement. But to single out potential energy is dangerous, okay? Is it electrical to mechanical? That's for motors, not generators. So that is incorrect. Heat to mechanical, well, that's absolutely ridiculous. We don't really care about what type. So no. And the worst part is that we're not trying to create a motor. It somewhat wants to go to the motor effect of some sort, but heat, nah. So our answer is B. Guys, it helps to just look around so that you are sure you are not being misled. It's easy, as you saw in the questions above. We easily got misled. And yet, if we thought carefully about the situation at hand and what actually applies to it, that's when you pick up the right answer. So don't be fooled by an easy looking answer. It may actually be misleading you. Alright, 1.10 reads the energy diagram. Again, guys, not quite a common question. Don't know when was the last time I saw a question like this in these recent exam papers you guys have written. But it's something worthy of looking into. Okay, there's a lot that can be said about it. Alright, for an element is shown below. Right. So it holds the electron transmission. It can't be transmission, but rather transition. Okay? Yeah. A from E2 to E1. By the way, usually these are negative. Usually these are negative. And the question is why? Remember, electrons closest to the nucleus have very strong attraction to the nucleus. So it needs a lot of energy to strip them away or to move into other orbitals. So in essence, so we need to expand energy to move those electrons. Hence, we regard this as a loss of energy in a way. Okay? Whereas those that are in the higher or highest energy levels, technically their energy is somewhat zero, isn't it? I think so, something like that. But yeah, I forget the actual thing. But read, guys, read, so that this thing is on point. Okay, so we're told that this transition from E2 to E1, we know that when we drop from a higher energy level to a lower, we will emit a photon of light. Okay. So there's going to be a photon emitted. So we are told that this corresponds to a green line in the elements spectrum. And what spectrum is this supposed to be? Emission. It's an emission spectrum. So that would be an emission spectrum. Okay. So we're told this corresponds with a green line. Okay. But then we look at this. The difference here is fairly small. Okay. We can just say fairly small. That means from the top to this E1, it's not quite a big difference. Okay, we're told this is corresponding to the green line. Remember, on the visible spectrum, we've got what we call Roig beef, meaning red, orange, yellow, green, blue, indigo, and violet. Now, towards this end, it's the invisible spectrum of UV light, ultraviolet, you name them. X-rays, a lot of those ones, high energy stuff. And to this side, it's all these low energies that we cannot see as well. They're too low. This is when we talk of infrared, things like that. All right, so this Roig beef part, this is the visible spectrum. And if we look at green is over there, sort of like in the middle. It's the middle type of energy, if I was to put it that way. Okay. Now what else are we saying now? The transition B, now we can see we're moving from a lower energy level to a higher. So we are absorbing energy. Okay, but if we look at this difference, guys, it's quite significant. Significant energy absorption here. All right. Okay, so we are told that this transition B from E0 to E1 corresponds to there. Okay, first of all, it's going to be an absorption spectrum. It can't be emission, so it has to be absorption. Anything that says emission is already dead and buried. But now the question is, are we absorbing green light or are we absorbing red light? Well, we can see that the energy that corresponded to green light was fairly small. This is an absorption of a very large amount of energy, and seeing green is intermediate. This being quite big, it means we are looking at this side. So if we said blue, indigo or violet, I would accept, especially blue, because it's somewhat closer. It's somewhat closer. Perhaps blue, it can't be green light. No. So technically here we don't have an answer, because look, red is totally wrong as well. Because remember, red is over there. That's a low energy. It should be even smaller than that of green. So this is not possible. So technically there's no answer here, guys. But then what do you do under these circumstances? You pick the best. What is closest to being the correct answer is B. But perhaps there was a misprint here. Maybe the typist put green instead of saying blue, because the most likely one is blue. Okay, so this is what we're supposed to see, because remember, when we absorb this much energy, we should be absorbing energy significant enough to have been one that can emit a blue light. So in a spectrum of this atom, we'll start to see energy on the blue spectrum that would correspond with this disappearing, becoming blank. Okay, so folks, this is essentially how it is. Again, even when there is no answer, folks, and you're very sure, please go back to instructions. You see, instructions sometimes are easy to forget. Remember, an instruction is given here that will answer all questions, irrespective of whether it's correct or incorrect. Not answering is dangerous in that, let's say the examiners realize that there is a mistake, or even to say this is a deliberate move to give a question without an answer, just to test if students are going to select an answer anyway. But even in your selection, students, please try to select something better than the rest, even if it's all hoax, but choose a better hoax, right? Because then when marks are awarded, even if you chose the very wrong answer, you will get marks. But those who don't choose, even when marks are to be given, they do not get those marks, okay? So don't lose these marks out of, being emotional in the exam. Stuff happens, sometimes deliberate, sometimes it's an honest mistake. Okay, please know one thing about these series. You see, when it comes to this kind of a situation, just know what is a Balmer series. Let me write it nicely. Please know this. What is a Balmer series? Know what is a Paschen. Okay, and also know what is a Linnemann series. Okay, obviously I can give you this one. This one is just the spectrum of visible light. So it's those Roig beef, it's all those energies. Then the Paschen series is basically those invisible low energy levels like infrared and stuff. The Linman series is that of high energy extremes on the blue end of the spectrum, like those UV lights, you know, X-rays and whatever, gamma rays. Please know these things because you may find yourself challenged with concepts relating to this, and you don't want to be caught pants down. Okay, now let's get to these structured questions and see what we can do. Okay guys, question 2 reads, a block of mass 5 kilograms and block C has mass 3 kilograms. Okay, good, we can see that. Block A is applied on a rough table. Okay, rough suggests there's going to be friction with a coefficient of static friction of 0.2. Okay, right. Once we talk of static friction, we know there's no movement here. Block A and block C are connected via a light inextensible rope over a frictionless pulley, and block B is placed on top of block A as shown in the diagram. Okay, that's it. Not a problem. We're told the system is only just at rest, meaning we are at Fs max, meaning we can surpass this. So can you see there's always indication? Can you see in the MCQs we dealt with static friction, which was rather not maximal? This time it is maximal. There's always information that can assist one to understand better what's going on. Okay, and on the point of sliding, can you see? If we just add an extra force here, everything is going to start going all haywire. All right, define the term normal force. Okay guys, definitions are unforgivable to not know them. So let's look at this. Question 2. So 2.1, we want the normal force. We can say it is a perpendicular force exerted by the surface on an object that is in contact. That is in contact with it. Okay, very important. Now the key stuff is that it is perpendicular to the surface. It is exerted on an object in contact with the surface. Okay, very important stuff. So easy 2 marks there. Nothing to lose. Okay, please guys, revise definitions if you find yourself feeling a bit weak. Determine the tension in the string, okay, while the system is at rest. All right, not a problem. Now we can see that the best mass to use is the 3 kilogram mass. So if we just draw a nice force diagram here, we will see that we've got its gravitational force straight down, and we've got the tension straight up. Now if this is at rest, it means the tension is equal to the gravitational force, right? Now using Newton's second law, we know that the resultant force is equal to ma. At this point, we don't care which one is bigger, they are equal, so you can say minus mg is equal to ma. So this implies that T minus the mass here, this is 3 kg, right? So this is 3 into 9,8 equals 3 into 0 because it's not moving. So therefore our tension here is going to be 3 by 9,8. Let's put it there. So we get 29,4. Now here's the catch. We were told minimum 2 decimal places. So you need to add this one, okay? Newtons. Is that all? Remember, this is a vector. Upwards. Or perhaps you can use an arrow. But for a vector, and having not been asked for just the magnitude, we need to give everything. Otherwise, marks can easily be lost. So of course, formula, we get a mark, technically calculating mg, and the final answer. But remember, the final answer gets a full mark if the unit is given in the, the magnitude is correct. 2 decimal places, when there's a decimal, we've got a unit. Again, it should be the correct type and direction. If any one of these 3 is missing, those marks are lost. In fact, 1 mark is lost. Very important, guys. Of course, one can just easily say this mark here is purely for just general substitution, since there's 2 important things: calculating the weight as well as knowing the acceleration is 0. So 2.3. Now we need to draw a labeled free body diagram showing all forces acting on block A. Easy. So there's our dot or plot. We know that first and foremost we're going to have gravitational force. That's Fg, but that doesn't look straight down. It is slanted. Okay, we've got Fg, and we know, okay, maybe let's do it this way, because there's 2 forces down. We can say perhaps Fg from this corner, right? That's the weight on the object of B. But we have another force. So we can just say this is the force of B on A, okay? Because that's the force applied by B on A. And then we're going to have a normal force. Okay. And we've got our static friction, because there is friction to this side. Right, and then we've got our tension to the other side. Now all these labels, guys, are acceptable, so there's no need to write in full here. So this is a mark, that's a mark, that's a mark, and. So we can see easy 5 marks being showered to students. All right, can I squeeze 2.4 here? We need to calculate the minimum weight that block B needed to prevent block A from sliding. Okay, not a problem, but perhaps let's answer this question separately. So we've got 2.4. Right, if we can just draw what is going on here. We've got these 2 guys. Because I'm going to show this a bit different. So this is A, that's B. And then we're going to have the weight of the 2, Fg. And we're going to have the tension. At this point, it's just a sketch, guys. It's not anything. We will have normal force. And we're going to have friction, static. And we're going to have the tension in that direction. So for us to deal with this issue, is that we need to think about these vertical forces. Right? The vertical forces, especially the normal force, can give us an idea here. 2, we still need to consider our horizontal forces, because they give us something as well. So this is one of those diagrams that gets a bit complicated. Now, how do we make this argument work? We're given the coefficient of kinetic friction, so we can use the frictional force here to give us what we want, since we know that these two are equal. So we will have the value for the frictional force. So we can use the frictional force here. We know that, okay, all right, the frictional force here is equal to the coefficient of kinetic friction, static friction, sorry, times the normal force. Okay, great. Now we were told that the frictional force is balanced by the tension, so it's going to be 29,40. So this is 29,40 equals, the coefficient here is 0,2. But the normal force, remember, is going to be the weight of these two together, because again, these two are also balanced. So the normal force is basically going to be, let's do this, it's going to be these two masses added together. So this is going to be 5 plus, let's say MB, right? Then we're going to multiply this by 9,8. That's what's going to give us the value of our normal force. Okay, so we can see that this helps us to work out the mass of B. So we can tell that the mass of B is going to be 29,40 divided by 2, but we will still have to multiply that by 9,8, right? And then we subtract 5. So let's see, the mass of B is going to be what? So we've got 29,40 divided by 2 times 9,8 minus 5. Aye, masingaqhelwa kakubi ke ngoku. Itheni ngiyafuna ukuhlanyisa ke ngoku. Mayingandihlanyisi. This answer cannot be this small, man. Come on, what is this? Okay, let me think again. Did I do everything correctly? Let me see. What did I do here? Yeah, man, that was 29, Juna. 29,40 divided by 2 times 9,8. Why is it not giving me the answer? This is giving me answers I cannot appreciate, you see. I don't appreciate this. Okay, I don't know, guys, why it's not working, but it's giving me something I don't understand. I don't know to get it. Hukom, guys. I mean, the maths is correct, most. This we divide by that. Whatever that is, we divide by 9,8. Oh, okay. I see my problem. I ended up with a 2. This is 0,2. I was surprised. The math is correct, man. Why? 29,40 divided by 0,2 times 9,8. Okay, now we're talking. Minus 5, we get 10. Okay. So that's the mass, 10 kgs. But again, if we wanted the weight, we could actually FOIL this out and say this MB times 9,8 would actually give us the weight, you know? Yeah, because why should we suffer? I don't want to do 2 steps. Let's just hold on a bit. just a little bit. We can say the mass of B times 9,8 is going to be equal to 29,40 divided by 0,2, right? Right. And then we minus here 5 times 9,8. Okay. So this implies that Fg for B is going to be equal to, let's see, 29,40 divided by 0,2 minus 5 into 9,8. It gives us 98 newtons. Now remember, we were told the weight, and remember this is a force, so this should be downwards. Okay. Again, guys, a bit of creativity here, but somebody else can calculate the mass, and then I just saw that we actually have an opportunity to avoid doing two steps here. Right. So maybe we may even say, I mean, weight we know is Fg, but just for, can write weight of B. Unanimous. This is it. Okay, general substitutions. This calculation. Answer. And maybe that left-hand side. Of course, guys, the answer we know. We know that we need to have the correct unit, correct magnitude, the correct unit, and direction. If any of these are not showing up correctly, the last mark is lost, okay? Very important. Again, guys, very easy stuff otherwise. So this is a very easy 15 marks to score. All right, so I'll leave the rest of this page for you guys to maybe make your notes. I will have this document available in the description of this video. By the time this video premieres, you all will have this question paper together with this document right down there. Again, if you're not lazy, just go over the internet, STEM Physics, you can get a copy of this question paper. All right, so that's it for question 1. Let's look at question 2. All right, not question 2, but question 3. Oops. All right, so question 3 says a learner stands on a balcony 5 meters above the street and throws a ball A vertically upwards at a velocity of 5 meters per second. At the same time, another learner throws ball B vertically upwards from the street to an initial velocity of 8 meters per second. At an initial velocity of 8 meters per second. And of course, our golden statement, ignore the effects of air resistance or air friction. So what are we creating? VPM. And so we know that the acceleration here is G. Downward. Okay. Right, so we've got the sketch. And everything looks nice. All right, okay. Now we just get to the questions. We attack them straight up. Okay, define projectile motion. Okay, so this is motion of an object under the influence. Under the influence of the gravitational force only. Okay, very important. This is motion. Of course, it's going to be an object, whatever it is, under the influence of gravitational force only. So this is key, guys. It's very important. So easy to mark there. So 3.2 says calculate the maximum height above the ground reached by ball A. Okay, so we know that ball A is going to go tick, 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 reach its maximum height, and then perhaps come back down. Either gets caught or goes straight down to the ground. So the final velocity at the top is 0. Okay, now I think it's always important to indicate direction in these kinds of questions. So for 3.2 we can indicate that we're taking upward as positive. At least, even if we indicate right there from the beginning that is our choice, so that everything we do is covered in the blood of Jesus, isn't it? Okay, so let's see. We know that the final velocity squared equals the initial velocity squared plus 2 GS. I'm protesting, guys, that's why, so don't cry. So basically U means initial velocity. It's what you guys call VI. Okay, capital letter S, usually we use capital letter S means delta Y. Okay, just displacement. I feel like too many symbols make this whole thing very ugly. We need a clean equation. So I'm protesting, right? The final velocity is 0. Initial velocity was given as 5, then we square it. Plus 2g is directed down, so this is negative. And we're looking for the displacement. Okay? But now this looks like a 5. Ach, doch. Kanti thina ngawazubhala u-S naman. Yeyiwe naman sinhlanyisa man. So we know that this implies that our S is going to be minus 5 squared divided by 2 into minus 9,8. So let's see what is that. So this is basically 5 squared divided by 2 into 9,8. Okay, so we get 1,2 to 2 decimal places, 8 meters. But remember, this was maximum height above ground. We can say then, we know that the height max is going to be the 5 meters that was there plus 1,28, which is going to give us 6,28 meters. Remember, this is a scalar quantity, so we don't worry about direction. Okay, so guys, this is good. Substitutions, good. And the final answer, okay. The intermediate answer was not necessarily required, but it was our means to an end. Easy 3 marks there. So let's look at 3.3. We're told to calculate the time at which the two balls move at the same speed. Okay. So we know that ball B is going to do its own thing as well. Tick, 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 reach its maximum height. We don't know where. And then come back down. So if it left at 8, it's going to reach at minus 8 meters per second. At its maximum, it's going to be 0. So the issue is, are they doing it here? Maybe. When the other one is on the way down and the other one is on the way up, it's not quite clear. We cannot tell. But what if this happens when this one is here and that one is there? We don't know. So I think a displacement versus time graph cannot really give us a clear picture, because this is not about the height. That means they are going to be the same. But I think a velocity versus time graph can give us a clear picture. Let's just try for a velocity time graph of these two, so that at least we have an idea of what is going on. Velocity in meters per second, time in seconds. Now we're choosing up as positive. We know that this first one is thrown at 5, so it goes, reaches its maximum height, and then goes and reaches the ground. Okay, let's just say this is when it reaches the ground. All right. We don't know at what velocity, but we can safely say that's the one. Or in fact, let's not even be silly. Let's just do it. Say 5. There it is. We don't know. Reached the ground, didn't reach the ground, not a big deal. So it started at 5. Okay, so that's fine. And then let's do the velocity time graph for B. B started at 8 and perhaps goes as well. We don't know at this point where does it go. What we care to do though is that these are accelerating the same. These must be parallel lines. Now, let's just extend this a bit to assess this nicely. Now what we can see, guys, is that before this one reaches maximum height, this is ball A, this is ball B. Of course, it started at 8 meters per second. And we know that ball B will reach the ground at another 8 meters per second, but obviously we don't know the other one, at what velocity it's going to reach the ground. Okay, but now what we can see here is that technically we can see that as this one reached its maximum height, if we can just shade that part, you know, as the other one reaches maximum height, meaning ball A, right? What we can appreciate is the fact that there's no way these two can have the same velocity, because for each one of these time intervals, this one is smaller than the other one until this one reaches maximum height. So which goes back to saying there's no point before the first ball reached maximum height where these could be moving at the same velocity. And we can even go on and say, if we explore this further, we can see that, again, when this one reaches its maximum height, there, and of course we incorporate all the other times after that. Okay? When the second one reaches its maximum height, we can also see that for these time intervals, this velocity of this ball is always greater than that. So it's always going to be great. So there's no way they will be moving at the same velocity after this ball has reached its maximum height. So it cannot be a situation over here and there maybe. So this means our time interval is definitely between this one coming down while this one is approaching its maximum height, which means that in a way could be a place for us to look at. And in this graph, we want to look at this region. In this region, is it possible? Well, it is possible. Why? Because if we say this velocity here, let's just imagine if we can say that velocity there is equal in magnitude to this velocity over here. Right, maybe it's not nicely shown. Okay, you see this could be, say, x, and then this is minus x. Yes, in magnitude these two are equal, but in direction they are not. It's possible that this can happen. Ne? It is very possible. So this is to suggest that, okay, maybe let's do it a bit better. It doesn't look right at this stage. So when we take this one down to the other one, we can say it's over here. It is possible that this could be x, this could be minus x. Suggesting that it's possible. So we have to look for that time interval between ball A reaching its maximum height and ball B getting to its maximum height. There is a possibility where these two could be moving at the same speed, because remember the question was speed here, not velocity. And speed is just the magnitude. The direction, we can tell this is opposing directions. So unfortunately, these are the types of questions that I would call higher grade, because a lot of thinking, guys. Because remember, if you cannot picture this, it's not going to be possible to perform the right operations. So picturing this a bit helps a lot. And sometimes whatever you've used, we can think about it that way. All right. So let's get to business here. That, okay, what guides us is the velocity time graph here. Sometimes you can even provide that sketch here and say, okay, this is where this is possible. I'm not too sure. Maybe let's draw another sketch. We can just say velocity time graph of A and B can give us an intel, right? Let's try to make it nice this time around. Of course, guys, this is just a sketch, but I'm going to try and make it make sense. Time in seconds, this is the velocity. In meters per second, that's 0 Mach. Okay. So we know that we can say this is the velocity of ball A. Okay, then we can say that would be ball B. Of course, we need to make sure that these are essentially parallel. Okay, so at this stage, we're just interested in what we want. So we can say this is A, this is B, this is 5, this is 8. And we are saying the time interval that can answer the question is this time interval between the two maximum points. So it is possible to get, say, if we draw a vertical line here, right? It is possible. Move it a bit in. You know, right around here, we can picture something that can answer the question. We can say this is the time t that we're looking for, because we can see that directly across, the other one would be moving at that velocity, and this one would be moving at that velocity. And of course, that is just a means to an end either. So we can say if that is x, that should be minus x. It's possible. All right, so we can see that that is the story of our lives. Okay, guys. So with this in mind, remember, try to show everything you have used in determining your answers to avoid being punished. Also to portray that you're actually thinking. Because there's no story that says you cannot do a velocity time graph when it is not asked. If you can use it to solve the problem, why not? Just like the position time graph, which is very popular. But you could see that it somewhat gave us an indication of what is possible, but we could not be so sure. But as we gravitated towards our velocity time graph, we started to have a clear picture of how this thing is supposed to work. All right, now we can do this and say, okay, for ball A, we know that the velocity that we're talking about, in fact, we can just use our standard equation. V is equal to, maybe let's start with ball B, because ball B is the big boy, isn't it? The big bad boy. For ball B, V is equal to U plus GT. Now this implies that V is going to be equal to 8 minus 9,8t. That is equation 1. Okay, then we look at ball A. For ball A, it has to be this negative velocity there. So we can tell that this is going to be minus V is equal to U plus G delta T. Okay, so that implies that V is going to be minus, the initial was 5. Sorry, this is going to be minus 9,8t. Therefore, our V here is going to be minus 5 plus 9,8t. That is equation 2. Okay, now we know that basically equation 1 is equal to equation 2, right? Because they each represent our variable V, right? It is like this. So we know that we've got 8 minus 9,8t equals minus 5 plus 9,8t. When you move things around, 9,8 plus 9,8 is 19,6t equals. We move 5 to the other side, it's going to give us 13. Therefore, t is going to be 13 over 19,6. What is this t now? 13 divided by 19,6 gives us a 0.66 seconds. Okay, so that's the answer that we get. That's the time where these two could be doing the same velocities, although in opposing directions. Again, when we say speed, we don't care about direction, but we care about magnitude. Okay, this one was a bit tricky. Technically, this is a tricky question. In fact, near impossible for a common matriculant, because you always think of the position time graphs only. Sometimes you forget that this can also give an indication. And again, understanding this comfortably is what is needed as well, so that you can be able to exclude these regions that cannot answer the question and narrow it down to the one that actually answers the question. Okay, that's all right. We can stop there. I can accept this. But again, you may think, is this true? We can check by calculating the maximum height time for ball A and calculate the maximum height time for ball B, isn't it? We can do that. So we know that V equals U plus GT, and this is 0 equals 5 minus 9,8t. Therefore, our t there is going to be minus 5 divided by 9,8. Let's see. Minus 5 divided by minus 9,8 gives us a 0.51 seconds. So we can see that indeed that is before 0.66. So Let's look for the other one. The other one, its time is going to be minus its initial velocity 8 divided by minus 9,8. Let's see what that is. Minus 8 divided by minus 9,8. That gives us a 0,82 seconds. Again, this is greater than that, so this means our answer is bulletproof, although it looks illegal. But everything, once we understand our work, folks, we can be sure that, okay, we've done it nicely. Okay, we get a mark for this. Deriving that equation, and that equation is key. Equating the two here is the method of solution. That gives us 4 marks. Okay, where is the 5th mark? Remember, sometimes a formula does get a mark. Okay, it can be formula. This is not necessary, but it could be looked at if, of course, you fluff the calculations and stuff. All right, that was quite a nice question. I never thought of it like that, but yeah, it works. When it works, guys. All right, so let's look at the next one. All right, 3.4 tells us that ball A reached maximum height after 0,51 seconds. We just confirmed it. Calculate the velocity at which ball B was moving when ball A reached its maximum height. So on our sketch, we are suggesting that we want to know at this time interval, what was this velocity for ball B? Okay, easy. So we know that V is equal to U plus GT. That means V is going to be 8 minus 9,8 times 0,51. Okay. Therefore, our V there is going to be 8 minus 9,8 times 0,51. We're getting 3 meters per second. Essentially, the decimals are insignificant. We can forget about them. We don't need to write 0, 0 here. Okay, so this is good. Now remember, the question said velocity. Now we see the answer is positive, so this means it was upwards. Be very careful of these questions, guys. It's easy to lose marks here. So we need the correct unit, correct value, magnitude, the correct unit, and the correct direction to score our last mark. And of course, here we can mark the formula, or we can mark the substitutions. At the end of the day, we're just getting 2 marks. All right. So let's see, 3.5 says, sketch the velocity time graph. Okay, it says here, sketch the velocity time graph for the motion of the 2 balls until they reach the same speed. Clearly indicate the following values on your graph: initial velocity of both balls, time at which ball A reaches maximum height, and time at which these balls reach the same speed. Okay, not a problem. We need to write the topic. Velocity, time, time graph of balls A and B. And of course, we can indicate that we took upward as positive, just in case, you know. Okay, so we're gonna have here time in seconds. Velocity in meters per second, that's the 0 mark. So we saw that this one started at 5, did its own thing, and then this one started at 8 and certainly did its own thing. It's not nice there, maybe let's take it a bit higher. Okay, let's copy this one. What on the Lord's earth is that? Why is it posting its own thing? You can't post your own thing, man. You ain't allowed to do that, okay? So we know that they will reach the same speed before this one gets to maximum height. So we can push it back and say, hold it back when you are not allowed to be here. Okay, maybe let's say, is it possible that it goes down there? Yeah, doch, not exactly. Okay, let's just see. Let's draw a vertical line and move it in. Approximate something here. I think this would be better. Yeah, that looks right. So we want to stop when they have those equal velocities. Okay. Okay. Right, so that is the story there, guys. So this one was 0.51 over there, and then here we've got 0.66 when they did the equal velocities. That was 5, that was 8. Okay, is there anything else missing? Maybe we can label this as A, that is B. Right. That's about it. That's about it, guys. So I guess we get marks for the shapes, and we get a mark for showing that time and this time, right? And yeah, any of the initial velocities. Of course, guys, if there's no label though, the axes are not labeled, the last mark gets lost, okay? So don't risk it. So this was a rather nice 16 marks, I guess. Needed a bit of creativity for 3.3. Yeah, a little bit of creativity is somewhat important, guys. I always tell you this. Keep an open mind. Otherwise, if you narrow your thinking, you're not going to win in physical science and maths. Okay, let's get to question 4. Question 4 says, a learner tests the strength of a piece of glass by dropping a steel ball of mass 5 kilograms from a height of 3 meters onto the glass. Okay. The velocity time graph below represents the motion of the steel ball from the moment the learner drops the ball until it reaches the ground. Okay, that's cool. We can clearly see that this is the impact time. So this is when the steel ball hit the glass right over here. Okay, so we can calculate that. 1 minus 0.8 is basically 0.2 seconds. Okay, that's the collision time. Okay, it's clear that downward was taken as positive here by the examiners, so we cannot choose otherwise. All right, okay. So first question, 4.1. To find the term momentum. we know that it is the product of an object's mass and its velocity. Okay, momentum is the product of an object's mass and its velocity. Don't know why my mass wanted to look like something else. So this is the product of the mass and velocity, guys. It's not a big deal. It is a vector. It has direction, right? Of course, it follows the direction of the velocity. I don't know, but the definition is just as precise as it is. Okay, it's an all or none type of a definition. It's either you get it or you don't. And if you don't get it, you lose marks. Eh? Okay, calculate the net force exerted by the glass on the steel ball. Okay, the net force exerted by the glass. But is the net force exerted by the glass? I'm thinking, yeah, it is exerted between the two. Newton's third law will tell us they each exert that much force to each other, okay? So obviously, guys, we're using the impulse momentum theorem. So this is going to be equal to the change in momentum. So the resultant force here, the collision time, we can even show it 1 minus 0.8 is equal to the mass of this object, which was 5 kgs, and its final velocity is 7, wait. Their final velocity is this one, the bouncing velocity. So this is going to be 1,53 minus the initial velocity, which is that which it arrived at the glass with. That's 7,84. So we can say, therefore, our resultant force. Why are you making me angry? Watla ho ntena mos. O nketsa diphahlo tsa hao jwale. Ska tlo nhlantsha wena man. 5 into 1,53 minus 7,84 all divided by 0,2 gives us a minus 157,75, which is going to be equal to 157,75 newtons. Now if this is negative, it's going to be in the opposite direction, so we took down as positive, so this is upwards. Some people choose to say just opposite direction, just to stay safe in case they made a mistake. But sometimes commit when you have enough information, but you may not commit if you're a coward. Sorry to face you like that. So that's good, guys. This is good. The general substitutions, the final answer. And as we know, the final answer, guys, yet again, we need to know that we need the correct unit in the correct manner. Not correct unit, but correct measure, correct unit, and direction. If none of those show up nicely, we nicely deduct that last mark and you go crying, okay? Hey guys, I had good news. You know, one of my students killed these prelims, especially chemistry. Wow, a straight 91. The student was on fire. Congrats, keep it up. See, this is what I want to see. When we do something, there has to be results, folks. So please, I plead with all of you guys, keep pushing. But remember, guys, it doesn't have to be a 91. If you can improve by even a 10% from your previous, usual mark, That for me is it's something worthy of a victory lap, isn't it? Because we're not different. I mean, we're not the same. But yeah, to see this kind of excellence again, it just shows, man, that we're doing good. We're doing good as a group. So let's keep up the good work, guys. Please, others, pull up your socks as well. No matter what results you get, as long as they are an improvement from your usual, that is enough for victory lap, okay? I'm proud of you folks. Very much proud. In fact, I'm more than proud. I don't know what to do with myself because of you guys. I torture myself for you. So when the results come, it even becomes all worthy. All right, 4.3 says, is this an elastic or inelastic collision? Refer to the data in the graph and the relevant principles to explain the answer. Okay. Right, so 4.3 is one of those higher grade questions where we commit to something. And again, guys, this is one that applies negative marking. So you either get it or you don't. If you make the wrong choice between elastic and inelastic, no matter how well the explanation comes up, it doesn't get a mark, okay? So watch out. So we can say this is an inelastic collision. Inelastic collision. Nah. By the way, how do I write the thing? Yeah, it's an inelastic collision. Why? We can see that the velocity with which the ball reached the glass and the velocity with which the ball bounced off the glass is different. And if that's the case, it means we lost kinetic energy. So kinetic energy was not conserved. That's the principle that this is being reserved. Okay, so we can say the ball reached or maybe we can say collided. Oh, I mean, English is English, guys. What can we say? The ball collided with the glass at a higher velocity than the one it left with. Okay, that's bullet number 1. So this means the ball lost kinetic energy. Right? And essentially kinetic energy of ball is not conserved. Therefore, therefore, the collision is inelastic. Okay, remember, guys, with every little bit of statement that you give, we need to see a final conclusion. Yes, the final conclusion is the same as the choice at the beginning, but we need to see it. We need to see it, okay? So this is an inelastic collision. That could be a mark. But if I say 4 marks, we didn't have to say a lot. So perhaps 2 marks for the choice. It's possible. And then if we say this collided, and I mean, we're explaining what happened here. So saying this has lost its kinetic energy, meaning kinetic energy was not conserved. That's a mark. And using the data as we were told, we can see that the velocities are different. So that's 4 marks. Again, how this mark distribution is to be made. It's not a big deal, guys. If you put a nice argument with a very clear argument and an end point, a very clear conclusion that is coherent with your argument, that is enough for full marks, okay? Right. So again, this one applies negative marking, guys, so watch out. Don't make a mistake of choosing a wrong collision and then explain the right collision. You will get 0, okay? The brutality here is severe. All right, so we are told that the glass does not break when the learner drops a soft rubber ball of similar mass from the same height onto the glass. Use physics principles to explain this phenomenon. Okay, again, here's another higher grade question where we need to explain. Again here, guys, one can actually calculate the sum of kinetic energy before and demonstrate that it's not equal to the sum of kinetic energy after. Okay, that's another way of explaining the first one, not this one actually. That's a way of answering this one. As I said, anything, either you're strong with words or you're strong with calculations, but do whatever you can do. Okay, so what are we saying here? Obviously, folks, here we're told that the glass does not break when the learner drops a soft rubber ball of similar mass, okay, and the same height onto the glass. But one thing that we're not told, which worries me a bit, is the change of of momentum. Are we experiencing the same change of momentum? Because this is a very challenging position that we are being placed. Yes, the velocity with which it reaches the glass is going to be the same, right? But then what is the velocity that it bounces off with? You know? So that for me is a bit challenging to figure out. It's a bit problematic because we know that our resultant force is nothing but equal to the change in momentum over time. And we know that the rubber ball is going to deform when it hits there, and so it will increase the collision time. Therefore, we can clearly see that force is inversely proportional to time, provided the change in momentum is constant. If the change in momentum is not constant, then we have a problem, you see. So, you see, these kinds of problems provided in here is a little bit hurtful, is it not? Yeah. So we're not given enough information here, honestly speaking, to provide an answer. But again, we have to answer, right? So we can easily say, okay, fine, we're going to assume that the change in momentum is going to be the same, although we don't know, because the bouncing of velocity can very well be different, especially knowing that the collision time is going to increase. Remember, velocity is a function of time, right? And here we're losing velocity. So if we're losing velocity over a longer period of time, as you know from this equation, v is equal to u. This time we're going to say minus at, because there is deceleration, isn't it? So the longer we decelerate, the longer we lose this velocity. So velocity is not going to be essentially the same if we're only using time alone, you know, for this explanation. So this is what hurts a bit. This is what hurts a bit, because this impulse equation is not helping to technically formulate a correct, answer. Hate questions like this, though, when things are not nicely put to us so that we can work. Again, a rubber ball may very well come up with the same velocity that it left. That it hit this with. We don't know. So there's a bit more to consider, honestly speaking. there's a bit more to consider. This one is a bit difficult to answer, you know. But maybe I'm overthinking the question. It's possible. But I'm kind of feeling, I don't understand. How will I survive here? Excuse me. And it's just 3 marks, folks. And again, you don't want to leave these 3 marks unattended, because you know what? These are just easy marks to score, folks. And unfortunately, we cannot escape these questions where we have to put up some explanations and all. We just can't. Yikes. What do we say? What do we say, folks? Because velocity here is certainly not gonna, you know. Oh no. This is not cool. This is not cool. So you see, with the right knowledge though, you can tell here that there's gaps with these question papers, which I don't like, because whoever designs this question paper somehow is just not careful. In all these provinces, there's always something not right. And it just speaks to the fact that, guys, I will sure we appoint the right people though for these jobs, because I mean, we can't keep having these things all the time. It has to be once in a while that, you know what, I mean, ilihlo liqothwa lijongile andithi kodwa awuzongixelela uzohlala uxotshiwe wena. No man, sisinoba umuntu onjalo, sisiyatha. I'm sorry guys, but you know what, this makes me unhappy now, because the principle here is the impulse momentum theorem here, but we need to be sure about the change in momentum. Is it going to be the same as for the steel ball? That's a problem. That's a problem, because even if it's to be the same, the problem is that the velocity is not going to be the same when it bounces off, because we see that once we stop for longer, because that's the idea. Once we decelerate for longer, we're going to lose the velocity much more. And as a result, this whole thing becomes a mess, you know. Maybe we can just say, assuming that the change in momentum is constant or remains the same, is the same as before with the steel ball, right? It is such that the collision time will be increased to more than the 0.2 seconds. That's number one. And we can say technically the resultant force on the ball will decrease since the F resultant is inversely proportional to time given by IF resultant is change in momentum over change in time. Okay, so I would say with the assumption, of course, I don't have a choice, guys, because I'm definitely making an assumption now, because I cannot answer this without this assumption, you see. Because in reality, if we don't try to create a scenario where this doesn't happen that way, this kicks in and it just says the change in velocity is going to be different. And if that's the case, we cannot assess the relationship between the force and time, unless I am missing something. Anyway, so this is the attempt to answer even when the situation is not allowing, guys, but be as clear as possible. I know some people will be careless because they will look at the memo. I mean, usually STEM physics papers have a memo. So what I would say, some markers, if at all, they would look at the memo before they understood what the argument put forward by the student is. Then they would see perhaps something that looks right according to the memo, but perhaps not carefully thought out, you know. Anyway, whatever it is, guys, so the resultant force, we can say, therefore, the glass will not break as the force applied by the ball will be less, right, according to Newton 3, because remember, this resultant force on the ball is going to be the same as applied on the glass by the ball, and if it is less, definitely it's not going to break. But again, there's a bit of work here that needs to be thought about. This question for me needs a bit of a discussion and a careful analysis to essentially determine if it is appropriate like this, because it's not giving the right vibes. Anyway, again, maybe let me write in words here that the change, assuming that the change in momentum is the same, not, okay, is, oh guys, this one is making me lose time now. Okay, anyway, folks, I don't know what would happen because this is punishable. Ideally, we should refrain from assumptions, but what do we do when we are not given information properly? We have to live with the assumptions. You see, the problem is happening again. In the MCQs, we had to assume. Now again, we're forced to make an assumption as well. Anyway, guys, this one is good. And to say the resultant force decreases and putting a proper justification for it, and using Newton's third law as well to explain why the glass will not break since the resultant force has decreased. Perhaps it makes a bit of sense, but we have a bit of an issue with the assumption. Sometimes you can lose a mark for the assumption. Maybe there's something better that can be used. I don't know. For me, this is the best I can do under the circumstances, because remember, guys, we need to remember the instructions tell us clearly that we have to answer all questions, no matter what strife or frustrations we have with the questions we just have to answer. Okay, so here we can say 13 plus or minus 1 mark or so. Not 13 plus, in fact 13 minus 1 mark possibly, because we would not lose everything, but 1 mark can be lost unless, honestly, this is very clear enough for a student not to botch, then the punishment comes for the student. Okay, let's get to question 5. Right. So question 5 reads, a motor is used to pull a crate of mass 60 kilograms up a 30-meter rough slope, meaning it's going to be Fk. The motor is connected to the crate with an inextensible rope of negligible mass running over a frictionless pulley. The slope is at an angle of 25 degrees to the horizontal. The crate starts from rest. Now, if it starts from rest, initial velocity is 0 and reaches a speed of 7.5 meters per second at the top of the slope. Okay. The crate experiences a constant frictional force of 16.2 newtons. Of course, that's the kinetic friction. Okay, good. Now there's the sketch, nothing to worry about. We know how to deal with forces acting on an incline. We know that there's going to be gravitational force, and there's going to be normal force, and components of the gravitational force, you know. Okay, so stuff like that is not looking very nice, but yeah, guys, these are perpendicular, and then the 25 will be the same as that. This would be FG perpendicular, FG parallel, normal force. We need to always think about those forces, okay? Right, first question, define a non-conservative force. Easy stuff. So we know that it is a force whose work done on an object depends on the path taken by the object. Okay, easy. So basically it's a force. Talk about work done on an object depends on the path that is taken by that object. So things like friction, you see. Yes. So again, it's an all or none type of a definition. It's either you do it or you don't. Now we're told to use the work energy theorem specifically to calculate the average power that the motor must provide to pull the crate up in 2 minutes. Okay, that's not a problem. So obviously we need work done by the tension, because there's going to be tension here and there, and because this is a frictionless pulley system, these two are equal. So if we're saying the motor, power done by the motor, we want actually work done by the tension. But if we're going to use the work energy theorem, it means we need the tension. Of course, we can just draw a nice sketch and say, fine, we understand that the force acting in this direction is going to be the tension, and FG parallel is going to work in that way. And of course, it's going to be frictional force. It always opposes motion. So these are the forces that are actually at play here. So this is what we need to consider. So we know that the total work done is going to be equal to the change in the object's kinetic energy, because we are told what to use. So this implies that we've got the tension minus the FG parallel, minus FK is equal to, wait a minute, Remember, this is the resultant force. Then we multiply by delta x cos theta equals half m v squared minus u squared. Okay. This is unfortunately the torture we need to endure. We need the tension minus Fg parallel. We know that it's going to be the mass of the object is 60 times 9,8 times the sine of 25 degrees. Minus, we were told what this one is, 16,2. Then the delta x is 30 meters. Then cos of 0 degrees because it's doing work in the same direction as the motion. So this is going to be half of 60 into the final velocity there is 7,5 squared minus 0 squared. Okay, very long lengthy little thing here, but let's go for it. So this implies, okay, what we can do, we can just pull this apart. I mean, cos of 0 is 1. So we can just move things around a bit, you know. So basically, we know that our tension here is going to be equal to, let's sort up the right-hand side. So this is 0,5 into 60 into 7,5 squared. Basically, this gives us a 1,687,5. Then we're going to divide by 30. Cos of 0 is 1. Okay, we can do that. And of course, we're going to add 60 into 9,8 sine of 25 degrees, and then we add the 16,2. Let's see what is our tension. So divided by 30 plus 60 into 9,8 into sine of 25. Please guys, be very systematic here and careful. It can go very, very wrong. Plus 16,2. It can be very wrong. So I'm getting 320,949,5 newtons. Remember, we don't want to round off too soon here. We will end up with very horrible results. It's an intermediate step. So once we know the tension, we can now safely say then power is the rate at which work is done by the tension. So the rate is going to be the tension itself. So this is going to be the force. In this case is the tension. Delta x cos theta all divided by T. Now this implies that our P is going to be, the tension is 320,9495. Displacement is 30, cos is theta, 0 degrees, divided by time. We were told this is 2 minutes, so this is 2 into 60 seconds. Therefore, there is the power. Let's find out. So this is going to be 320,9495 into 30, essentially, divided by 2 into 60. So we get basically 80,24. That's watts. Okay, so that is not a problem. Power is a scalar quantity, so we don't worry about direction. Okay guys, so we have done our job. looks all right to me. Now, of course, we get a mark for the formula, right? What do we get? Sometimes there's so many things that have been done. We can say maybe the right hand side, you know, and say this too, and say the rest of the left hand side. Ish, guys, this one is torture, you know. What are we doing? What are we doing, guys? I'm thinking perhaps finding the tension is key. So 1, 2, 3, 4, 5. Oops. 6 and then 7. Really? Nah. I gave too many marks here. Maybe we can just say the whole of the left hand side here. You know. Here we can say formula, left hand side, right hand side, intermediate answer, 4 marks, 5, 6. This one really deserves a mark, okay? Alright, okay, alright. So again, guys, no matter what this mark distribution is like in the formal guidelines, we just have to do what we have to do. Okay, that's that for this. Okay, let's look this one up. We've got 5.3. It's one of those higher grade questions as well. In fact, 5.22 is not quite an easy one. Okay, will the work done by the motor increase, decrease, or remain the same? It's one of those all or none type of questions. Or remain the same if the crate is lowered down the same slope at the same initial velocity, initial and final velocities. Okay, explain the answer. Okay, so basically we've got our slope, but I'm not too sure what are we talking about. Is this 7,5 here and 0 there, or are we saying there's a reversal? 7,5 and 0. But again, if we say initial, perhaps that's the story. Okay. So it means we're moving this down the same slope of 25 degrees. So it's going to be going that way. So basically, if we think about it, the forces at play now for our block here, it's going to be tension this way, and kinetic friction also that way. Then there's only going to be FG parallel that way. But now we see that this is a constant. This is a constant. Now for these two together to add up to this constant, while this one maintains its value, this one has to definitely drop. So it's more of a logical thing, I guess. It's in papelo when. Okay. Right, so that is the story that we can put forward, folks. Remember, when we explain, we can use anything. Okay, so 5.3. I'm going to squeeze it here. Let's just showcase this force diagram, just to assist our markers as well, to see our thought process, wrong or right, we don't care. So this should be the tension. We don't know which one is bigger, and Fk. We can easily say here, well, it's going to decrease. Remember, the work done decreases. Why? Because work done is force times delta x cos theta. Yes, that's it. Now, this is constant, and we saw that the force has decreased, and we know that work done here is directly proportional to work if this remains a constant, which is the case. I mean, it only gets negative because negative in that it's in the opposite direction now, because cos of 1/8 is going to give us that. But yeah, if the force decreases, the work done is going to decrease. So we're going to say decreases. Now, why is that? We can say, well, the FG parallel, okay, will be balanced by the FG parallel. Okay, we can say the parallel component of weight will be opposed by, actually FG parallel here is greater, right? FG parallel should now be greater than the sum of these two, Fk and the tension. It's not equal but greater. Is going to be opposed. In fact, we can say is greater. Okay, it looks like I'm squeezing myself here. I'm gonna end up in trouble, so let's just leave this small space. Let's leave it. Alright, so this is 5.3. Now we have a situation. If this object is gonna move down, it means FG parallel is greater than these two together, the tension and Fk. Okay, so we are saying FG parallel is greater than Fk plus tension. That makes sense, okay? We can say it will decrease. Move aside, you're not important. You're just a means to an end. So we will write here decreases. Okay? Why? We can say here the parallel component of weight of the crate will be greater than the sum of the kinetic frictional force and tension. The tension, and the tension on the string as these will be in the same direction. Okay, so we know that the parallel component of weight is going to be greater than the sum of the kinetic frictional force and the tension on the string, as these will be in the same direction, meaning they will be adding together. Again, this is explained by the fact that the object is going to be moving down slope, so it means the parallel component is greater than these two. We can say, since sometimes what is important is to then introduce certain things, but I'm sure everybody knows what FG parallel is. And when you say kinetic frictional force, we know what we're talking about, but I just want to be as complete as possible and say Fk. Then when I say tension, I want to just use symbols this time. I don't want to say anymore. I say T. Okay, so I can say since Fg parallel is constant and Fk is also constant, it follows that the tension, T will decrease. Okay? There's no way the tension will increase or remain the same but be less than the gravitational force. Remember, the initial tension was greater than the gravitational force together with the frictional force. So if the roles are reversed, it means the tension applied is going to have to be less, right? So if the case is like this, we can say then the work done by the tension, which is motor, will decrease as given by the work directly proportional to the force. In this equation, work is, maybe we can say, done by the tension is going to be the force by the tension times delta x cos theta, right, where delta x is constant, right? So guys, sometimes it really hurts, but what can you do? You just have to give everything, but make sure you make these bullet points as very comprehensive as possible. So we get a mark for choosing that. And of course, by stating that the tension will decrease, very important. And of course, this is the justification for that. And the work done itself, I mean, this should have been 4 marks to be honest. But again, we said it decreases. This time we're just providing, a more logical explanation for this. All right. Anyway, guys, all I can say is give your very best when it comes to these kinds of questions, because it's easy to miss the point, but try to carefully select your arguments and give the best answer you can come up with. Anyway, guys, this is it. I'm going to stop it here. My writing is horrible, folks, so I don't know if you're going to be able to read what I wrote. But I'm going to provide you with this memo, guys, so that you can say so unfortunately you will just have to combine this with what you hear me say, because honestly it is what it is, guys. Sometimes I write better when I'm not agitated, but when I am, it just goes very horribly. So I cannot control it. Anyway, folks, work energy theorem stuff, or work energy and power, it's a very popular topic, guys, and usually higher grade questions here like this do come. And as you can see, this is also a higher grade question. It needs logic this time, a logical connection of things. So you have to be very, very particular in how you select your argument and how you put it forward. Okay, let's get to the next. Get me the next page winner. So let's deal with this question 6. Okay, question 6 reads, a group of learners conducted an experiment to determine how the speed of a sound source moving towards a stationary observer affects the apparent frequency of the sound heard by the observer. The results of the experiment are shown in the graph below. Okay, what do we see? Well, we see that this graph at time 0, when we're talking about speed, so this is when the object is not moving. What was the apparent frequency detected here? Is somewhere here. Okay, now we need to find out what this is. Of course, we've got a small little scale here. So there's how many ticks? 1, 2, 3, 4, 5. So that means it's 10, 20, 30, 40, 50. We can just say 50 divided by 5. It gives us 10. Meaning the small tick is 10. So this is 150, 60, 70, 80. So this is 180. So the 180 hertz is basically the actual frequency emitted, because this is when the object is stationary. Okay. Then as it starts moving towards the listener, we can see the graph is climbing. Okay. Right. Of course, the apparent change is that there will be more compressions ahead of the source reaching the listener per second, and that would mean the wavelengths would appear to decrease. Since these are inversely proportional, the frequency will appear to be higher. Okay. It's a phenomenon. It's not a reality, right? Okay, that's why we call it an apparent change. Okay. So at least we know what is cooking here. Let's just answer the questions. 6.1 says, state the Doppler effect in words. Okay, so we know that this one states that the apparent change of frequency, or the Doppler effect is the apparent change. Frequency of sound as observed by a detector when there is relative motion between the sound source and the detector. Okay, so that's the thing, guys. A bit wordy. All I know is that it's an apparent change which is due to the relative motion between these two. Okay, very important. Okay, right. So easy 2 marks there. 6.2 says, write down an investigative question for this experiment. Okay, well, if you look at this one, it says how the speed of the sound source moving towards the stationary observer affects the apparent change. As long as the question cannot be answered with a yes or a no, it should be okay. Okay, right. So we can just say, how does the speed of a sound source, how does the speed of a sound source moving towards a stationary observer affect the apparent Come on now. The apparent frequency of the sound heard by the observer. Of course, we changed that statement into a question, so there has to be a question mark at the end. Okay, right? Of course, guys, you can ask any other question, but sometimes with the given statement it can be converted into a question. Easy 2 marks there, as long as this question cannot be cannot be answered with a yes or a no. Use the graph to determine the true frequency. We saw it. It's going to be 180 hertz. Now it's capital letter H, small letter Z. Please present this answer in the correct manner. Magnitude as well as the unit. 6.4 says, use the results of the experiment conducted at source speed 100 meters per second to calculate the speed of sound in air on the day of the experiment. That the experiment was conducted. Okay, so we take it to the graph and then we move across the graph. That takes us to 250. So that would be the frequency heard. It would appear to be at 250 to the observer. Okay, so this is the Doppler effect equation. Frequency of the listener equals V plus or minus VL divided by V plus or minus Vs times Fs. Okay, so we saw that we had 250, so V is what we want. In fact, our listener is stationary, so we're not going to consider anything there. So this is V, but when we want to make this one smaller, I'm going to subtract 100 times 180. Alright, so we can see that this is 250 over 1 equals 180 V over V minus 100. Cross multiply here, we get 250 V minus 250 by 100 is the same as 25 times 1. Then we just put all the zeros. It's 25 squared equals 180 V. Then we move things around. 250 minus 180. Okay, 180 plus what will give us 250, 70. Yeah, so that's going to be 70 V equals 25 squared. Therefore, our V is, when we divide 25,000 divided by 70, we get 357,14 meters per second. Now what are we solving for? A scalar quantity, speed, so we stop right there. Okay, so that's fine. So we get a mark for the equation, perhaps a mark for getting that guy, and then the rest of the general substitutions, and our answer. Remember, the unit has to be presented, the magnitude should be presented in the correct manner, as well as the unit. Otherwise, easy stuff here. Okay, 6.5. 6.5 says, consider the graphs A, B, C. Now, which of the graphs best represents the wave as the source approaches the listener? Of course, it starts off perhaps at a frequency that is rather less, meaning a wider wavelength. This one is constant. It's not possible. This one starts at a high frequency and evens out, not really. But it may start off as a very even frequency, but it gets higher as it approaches. So C is the best choice. So we can choose C. Now we need to explain. So we can say that as the sound source approaches the listener, there is more compressions of the sound wave ahead of the source, reaching the listener. Oh, Nkosi yami, khani ngithandazele le writing yami ibheda kakhulu man. Yes, okay, there is more compressions of the sound waves ahead of the source, reaching the listener per second. Okay, let's not make it too complicated. But again, per second, that's true, man. Per second. Maybe let's say per unit of time, but usually time we talk about seconds, isn't it? All right. Then this will translate to a higher frequency. Because once you say compressions per second, the more the merrier, then the higher the frequency. You can say the sound pitch, or maybe the frequency is higher. The frequency of sound is therefore higher. Yeah, I mean, guys, there's not a lot here than actually emitted. Maybe we can say higher than actually emitted. Right, guys, we get a mark for choosing a graph here. And talking about compressions, that gives us a bit of a mark. And then talking about the frequency essentially becoming higher, that's good. Of course, you choose your battles very well. Make sure that whatever you present, it makes sense scientifically and in particular to the phenomenon at hand. All right, guys, so that's it for the Doppler effect. Very nice and tasty, 13 marks there. Not a lot of sweating had to happen there. Okay, so question 7. All right, so it says 2 identical charges, Q1 and Q2, are placed on insulated stands. So in a way, we don't want any extra interaction. We're creating a closed system. Can you see? Or some kind of a vacuum. Now, these are placed 6 millimeters apart, so we don't work with millimeters. So this is 0.006 meters when we divide by 1,000. Do it immediately. As shown in the diagram below, right, we see that. Okay. I told you that the magnitude of the electrostatic force that Q1 exerts on Q2 is 3 times 10 to the exponent minus 3 newtons, and we're not told in which direction, okay? Point X is a distance d to the right of Q2, okay, cool. Now we need to state Coulomb's law. Easy marks. 7.1 says the magnitude of the electrostatic force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Okay, so that is the story, guys. So it's a very wordy thingy, but as long as we mention the magnitude of the electrostatic force between 2-point charges and mentioning the direct proportionality to the product of the charges and the inverse proportionality to the square of the distance between them, you can almost tell here that, yeah, it's very difficult to kind of say it differently, is it? Yeah. A very wordy one like this forces a little bit of more regurgitation than creativity, or else the sense gets lost. Anyway, if you forget this one, you just describe the formula Fe is equal to KQ1 Q2 divided by R squared. Now remember, guys, for all these definitions, if you actually look at the information sheet, pretty much all the formulae describe the phenomenon. So you can just describe that formula. You've got the right thing, except for this formula. F delta T equals like this. Now, with all these others, we always describe the right-hand side to explain the left-hand side phenomenon. But in this case, when we talk of an impulse, we only describe the left-hand side, never the right-hand side, because the unit here is Newton second. It's not kilogram meter per second, which is momentum. So that's just the only exception, which is very easy to remember. Okay, so 7.2 says a learner has drawn the following electric field pattern between charges Q1 and Q2. Okay, so what we notice with this is that the electric field lines are directed towards the charges. So normally that is the case of negative charges. Okay, now seeing that these electric field lines are actually not overlapping, definitely these are like charges and therefore they repel each other. Okay, so that's the little studying that we can do there. State whether the learner has drawn the electric field pattern for 2 positive charges or 2 negative charges. It's obvious. It's going to be 2 negative charges. Provide 2 reasons for the answer. Okay. Yeah, you guys are being punished here. I can see. Well, we can say the electric field lines are directed. The field lines. Let's say the electric field lines are directed to the charges. Number 1. Number 2, to show that the 2 charges have the same quality is that the field lines do not overlap. shows charges are of same nature. Okay, that's just too much information, but I think that's enough, guys. Making that selection, stating that these are directed towards the very charges, and to see that they actually don't overlap, then these are definitely like charges. Okay, or same nature, like or the same nature, whatever. Easy 3 marks, folks. Let's get to the next one. 7.3 says, calculate the magnitude of the charge Q1. Okay. Right. Well, we were told that these two are identical. Sometimes that word gets thrown carelessly. If no explanation is given, we'll assume that they are of the same magnitude. Okay. So we know that the electrostatic force here is K Q1 Q2 divided by R squared. We were told that this is 3 times 10 to the minus 3 newtons, right? This one is 9 times 10 to the 9 into Q1 squared, because they are the same, isn't it? We can make that assumption. Sometimes I don't like this question, 0,006. Then we square this one, because we're told these were 6 millimeters apart. So with cross multiplication, we see that Q1 is going to be equal to the square root of essentially 3 times 10 to the minus 3 into 0,006 squared, all divided by 9 to the 9. Therefore, Q1 is, remember this is a negative charge, so we need to show the negative. So let's see, square root of 3 times 10 to the minus 3 into 0,006. That could still be 6 times 10 to the minus 3. Make sure we square it, 9 to the 9. So we get a 3,46 to 2 decimal places times 10 to the exponent minus 9 coulombs. Okay, easy stuff. So it's nanocoulombs. All right, nothing big here. So we just simply substitute, plug and go, you know. Is plug and go type of a thing. Then substitutions here and the answer. Why are we getting 4 marks? Maybe for the sign? I'm not sure. Sometimes it's strange. See, this is a standard 3-mark question, but hey, whatever. Sometimes maybe it may be silly. You say, well, that can be important to give a mark for. Yeah, so, but remember guys, magnitude must be presented well with that negative sign and the unit. Important. Okay, so 7.4 says the electric field strength at due to Q1 only is 3,33 times 10 to the 5 newtons per coulomb to the left. But at what point? Calculate the magnitude of the distance d. Probably this is at x. Okay, this is missing. Very important, guys, for people to check, because sometimes, you know what, it's horrible. Okay, so this one we know that, well, the electric field is going to be, according to Coulomb's law, we're going to use it like so, right? So we are told what this is. So this is 3,33 times 10 to the 5 equals 9 times 10 to the 9. Q1, we got it, now it's 3,46 nanocoulombs, all divided by the distance is going to be first the 0,06006 plus x, maybe d, because that was d. Okay, yep, we've got it. Now we just have to do the gymnastics. So this implies that our d is going to be the square root of, we will take this there, divide by that, sorry, and then we take the square root and free this, so this is going to be 9 times 10 to the 9 into 3,46 times 10 to the minus 9, all divided by 3,33 times 10 to the 5. Then we subtract 0,006. Okay, therefore our d will be whatever we get. So square root 9 times 10 to the 9 to 3,46 nanocoulombs divided by 3,33 times 10 to the 5 minus 0,006. We get 3,67 times 10 to the minus 3 meters. Okay, right, that's not too bad. That's not too bad. It's 0,004 basically to 3 decimal places, you know. It's not bad. It's not that bad. It's actually good. Yo guys, kadimisa kuwenza lezi videos. Yo. That is the mark. Substitutions, how many marks? 5, and then maybe putting that in there. That's the one, and maybe, because usually with this too many marks in electrostatics, it doesn't mean there's a lot of work, folks. It just simply says we need to be careful about what we are doing, you know. At the end of the day, it is what it is, you know. It is what it is. Whew. I need a cup of tea. I'm tired. Let's just rush through the next one quickly. Then maybe I can make a cup of tea. Maybe chow something. At least if I can just leave 2 topics, then I know I am doing fine. So this was not bad, 14 marks. I hate electrostatics actually, because of these big calculations that irritate me. At least this one was not made to make that painful thing of finding the resultant and what. It gets very complicated sometimes. All right, let's chow question 8. Right. Okay, guys, I'm gonna do a bit more physics. You know, I want my students to master this thing. They seem to not like this physics thing, so I'm gonna give it to them. That is, I'm gonna give it to you. Now, question 8 says, in the circuit below, the battery has an EMF of 12 volts and an internal resistance R, so it's a potential question. The 3 resistors and the light bulb are connected as shown in the diagram, okay? The resistance of the bulb is 2 ohms, okay, it's indicated. Both switches S1 and S2 are open, you can see that. So this means initially there's no current flowing in this circuit. The connecting wires and the ammeter have negligible resistance. We know that this means it's too small, we ignore it. Okay, so again, folks, if we're to see the current flowing here, we know that the long bar is the positive, the short one is the negative, and the unit is a cell. So we've got 2-cell battery here. This suggests some home appliance type of a device here. Okay, the current comes out of the positive terminal. We call it the conventional current. Here it splits into this one and that one, right? Then it comes together again in that node, goes through that 6 ohm resistor, and then of course back. That's when the current is moving. All right, so we understand. Question says define EMF. Grade 10 question, is it not? Yeah, it's more like a grade 10. Remember, once you forget here, there's this thing, work done here is like this. So you just solve for V basic. V is, it is the maximum. It is the maximum work done by the battery per coulomb of charge. Exactly. It is the maximum work done by the battery per coulomb of charge, or to move a charge across the circuit. So it's as simple as that, guys. It's either you know or you don't. It's an all or none type of a question. There's no parts that can be considered here. All right, so 8.2 says with only switch S1, okay, this one. So it means our current is bypassing our light bulb or the parallel connection. So we're not going through there for now. Okay, so we need to calculate stuff. So 8.2.1. The reading on the ammeter. Okay, that's the total current. Yikes, that hurts a bit. What are we gonna do? Okay, we know that the total resistance here, at least the external resistance, is going to be the 6 plus that 6. Oh, we were told the voltmeter drops. I was wondering what's going to happen now, because we don't have much. Then that makes our lives easy, because if this is what this is, it means it's going to be the external voltage, meaning the total voltage for the external circuit. So we can say here V is equal to IR. Here the voltmeter is 10,8 essentially. It's going to be the total current. The resistors is going to be the 6 plus 6, because they become in series, these two. So we can say therefore the total current here at this stage is going to be 10,8 divided by 12. Let's see, what is it? 10,8 divided by 12. So this is 0,9. Please present the answer correctly, guys. I know the calculator is going to give you 1 decimal place, but we're told minimum of 2. That's where your students lose the marks. Please, magnitude must be correct. The unit must be correct. Okay, formula, general substitutions, answer. Why is the 4 marks? Maybe calculating the external, or even to know that that is the voltage we can use, perhaps. Is a technical factor. Usually with electricity, guys, the bigger marks don't mean the question is impossible. Just says it's a technical issue, so make sure you cover your bases, right? Now 8.2.2 says we need the internal resistance of the battery. Okay, that's easy. Again, we know V equals IR. Now this implies that V is the lost volts. It's going to be from 12 down to 10,8. equals the total current is 0.9, then times the internal resistance, that's the 1. So this implies that our small r is going to be 12 minus 10.8 all divided by 0.90. Therefore, our little r is what that gives us. Okay. So I'm getting a 1.33 ohms. Okay. Right. Okay, that's one. That one is also easy. Plug and go. Right. No big deal. Let's get to 8.3. We've got 8.3.1. So it says both switches S1 and S2 are now closed. The ammeter reading increases. Can you see? It was initially 1.33. Now it's gone up by some digits to 1.5. So the current increases. Rightly so, because we know that when we give this parallel connection its go ahead, this will drop the effective resistance here, okay, to be smaller than the smallest. Now these ones are in series, it's going to be 5 and 6, meaning it's going to be less than 5. Then we just add 6. Can you see the total resistance is going to be less than the 12 we had initially? It's going to be 6 plus something less than 5. It's going to be somewhere 10, 9-ish. So that's less than 12, and therefore resistance indirectly proportional to current. So what happens? The current increases. When the current increases, what's going to happen? This guy is going to chow more from this, meaning there's going to be less voltage for the external circuit. Okay, that's it. That's it. All right, so it says calculate the power dissipated by the bulb. So this means we need the current through that light bulb. Okay, I mean, don't get scared by this. It's usually not a big deal. Okay, what I normally would do, I would target the current by using the ratios. So I can say the ratio of resistors in parallel is, it's basically 6 is to 5, because the 3 and the 2 will add up to 5. Yeah? So it's 6 is to 5. So this implies that the ratio of the current is going to be like this for the parallel resistors. For the parallel resistors is going to be the reverse, 5 is to 6. Okay, it always does that. Okay, now we can say this implies that the current through the 2 ohm bulb is going to be equal to, remember that branch is the one that gets the most current. It's going to be the 6 over, we add the 2, they give us 11, we multiply by the total current that we were given. Therefore the current through the 2 ohm resistor is going to be, let's see, 6 divided by 11. Then we multiply this by 1.5. We get a 0.818 amperes. Maybe we can keep it to 3 decimal places. Okay, so that's the branch of the current that passes there. So we know that then power is basically I squared R, isn't it? Yeah. So this implies that our power is going to be 0,818 squared times 2. Therefore, let's see what this is. 0,818 squared times 2. We get 1,34 watts. Okay, good. To 2 decimal places. So this is fine, guys. Very easy stuff. When you know what to do, you just have a very easy way going about it. So this is a mark, this is a mark, this is a mark, this is a mark, this is a mark. That substitution is a mark. 1, 2, 3, 4, 5, 6. We can keep this one too. So easy 7 marks, guys. Of course, you can explore other ways, but you will see that other ways tend to be labor intensive. But in my opinion, when you're writing an exam, guys, study the diagram, see what you need, choose the easiest approach if you can find one. But if you can't, go for it, the long one. It's not a problem. All right, so let's do this one. 8.3.2 says, what effect will the closing both switches have on the internal volts? We know that they're going to increase, right? They will increase. And of course, we were expecting it. It's like Newton's laws of the electricities this time. There's always going to be stuff like that, work, energy, and all that. Anyway, so we know that it's going to increase. Right? How? We know that with both switches closed, the parallel connection will effectively drop the total resistance of the circuit. Circuit, they say. We know that. Now we can say the current, the total current, will increase since we know that current is inversely proportional to resistance. Okay, so if the total current increases, we can say again the lost volts will increase. Such that V lost is basically I torque times R, with R as a constant. Okay, so folks, it's very easy. We know that if the total current increased, this whole situation will increase, isn't it? Because the lost volts are directly proportional to the current. You can even put that one and say the lost volts are directly proportional to the I torque. If the I torque increases, that increases because the internal resistance is a constant, or basically logically from a calculation. Easy, guys. Choose the right thing. If you chose the wrong thing, already everything is lost. So these are the negative marking type of questions. And in essence, these are higher grade questions, guys. So be ready to explain as you would in Newton's laws of motion. So essentially, by stating the relationship of the current to the total resistance, and of course stating that the total resistance will drop or decrease. That was the key step. The rest is just to put it home, because we have to put it home. There has to be a conclusion. Whether it's going to get a mark or not, it's immaterial. Okay, so guys, that one was also a very nice and tasty 19 marks. I don't know why, guys, you were crying. There's nothing here. I don't see any stones, Moss. They have not thrown any stones, but there are mistakes, perhaps, in some questions. Unless I'm overthinking things. Again, guys, this thing comes with the memo, the official memo, so do have a look at it. Compare and contrast with my memo. But you see, I'm giving you my memo so that you can see how very close sometimes my arguments get to the official memo, although I did not make the official memo, although I do not even look at it, because what's the point? You see, we have to find the answers in the questions, because in the exams, guys, you're not going to see a memo to confirm that you did well. This is why I would rather you don't even worry about what the memo says. Worry about whether you can find a perspective in a question, whether you can answer that question adequately, and to even develop skills of checking if your answers are actually making sense in the given scenario, because that's the only way you would know you are right. That's why I do it this way. I torture myself so that you can see exactly what happens to you in the exam. At the same time, to show you how to worm your way around those entanglements, to get yourself free from the spider web and to stand victorious on the other end. Okay. All right, guys, so let me just drink something, chow a little something. I mean, it's late, but I'm hungry. So yeah, we're gonna get to the next questions quickly. All right, folks, so let's get to the next question. Try to run through it as fast as possible. Question 9. Question 9 reads, the simplified sketch below represents the structure of a motor of a cordless drill. Okay, fine. We see that there's a power source, even if it was not identified as a motor. This is enough to realize that this is a motor. Now 2, we see this lovely thing. It's called the split ring commutator. So this makes this one a DC motor. Okay. Right. So that's the story. At this stage, we don't know the polarity, but again, I'm looking at these arrows. these arrows. You see the force on this segment is telling us that the force here, the thrust is down and the thrust is up. So this means if we look on this side, remember for motors we use the left hand rule. So we'll have our left hand, the thumb is up, the index finger is like that, and then the other fingers somewhat curled like that. And of course, this middle finger is going that way. Right, so this is the current. This is the force or the thrust, meaning our coil is going to rotate anti-clockwise. And then this is the direction of the electric field. So if that's the case, it means this is the North Pole and that's the South Pole. All right, that's it. So we use Fleming's left-hand motor rule. Okay. Your knuckles there or anyway, anyhow, so let's see what is the story here. 9.1 with 9.1.1 says name the electrical component in the above motor that ensures that the coil rotates in one direction only. It is that split ring commutator. Even if you just wrote split ring, that's enough. Okay, great stuff. So 9.1.2 says, identify the polarity of the magnets A and B if the current flows in the coil as indicated in the sketch and the coil rotates anti-clockwise. Of course, those arrows already gave it away. So essentially we can tell that A is the south pole. And B is the north pole. Okay, because the field lines are always from north to south. Okay, easy 2 marks. Usually this section, guys, is just a popcorn. Okay, don't lose marks here. The maximum current output, see, maximum, of another drill operating on alternating current is 10.5 amperes. Now, if a current was just given without specifications of maximum, you always treat that as RMS current. Same with the voltage. If the voltage is not clearly defined that this is maximum voltage, you will assume that to be an RMS voltage. Okay, please remember that. Anyway, so we're told that a graph of potential difference output of the drill against time is shown. Okay, we can see that. And obviously we see that the peak is 300 volts. Okay, RMS volts is going to be somewhere in there, you know. So, but again, that's not the question. All right, so let's see, 9.2.1, we are supposed to define the RMS current. So we can say it is a current from an alternating, maybe we can even write from an alternating current source that would be an equivalent to that from a direct current. Okay, usually the direct current source is much more than the RMS one. Okay, again, guys, this one I'm quite shaky about it. I'm not as confident. I don't know when was the last time I checked this, so please be on the lookout. I'm just using my understanding right now, so please check it out so that you don't sit with this and say, but someone showed me this. Please check it out and confirm. Please make sure you know how to state it well. But it starts from understanding, though, to survive these kinds of questions. Okay, 9.2.2 says, calculate the RMS current. Easy. We know that IRMS is basically the peak, or should we say max, divided by the square root of 2. So this is going to be the peak current, which we were told is 10.6 divided by the square root of 2. You know, it's bad. When we grow up, we were told that the noise that it makes, in fact, that the bed itself is associated with evil spirits. So, you know what, I get a bit uncomfortable when I see this stupid bed. I've cut to 2 decimal places. This is what I'm getting. All right, folks, so this is can you see the IRMS is much less than the actual peak, which would be from a DC source. So essentially, that's just the idea here. Formula, substitutions, guys, and final answer provided. We present that answer as required by our general instructions. Okay, this one says, hence, calculate the average power generated by the drill. Okay, again, with power in this topic, it's going to be VRMS times IRMS. We don't use anything else. So the peak voltage there, we saw that it's 300, but we need to divide it by the square root of 2. We then multiply this by 7,50. Therefore, our average power is, can you see, guys, with electricity, it's like dealing with Newton's laws. There's always energy at play here. There's always energy at play. So this is 159099. Remember, this is watts. Okay, good. We're doing fine, folks. My worry was that time-ish. I tend to overly indulge, and I lose time. But hey, a review, guys, is always a review, is it not? Yes. So I suppose these are the marks that should be scored by a student. Okay, let's see, 9.2.4. Says, is the power generated by the drill at T1 a maximum or minimum? Because we've got a maximum stuff there. There is that T1 or whatever that is. So it looks like it's a maximum, hey? So we can say maximum. Sometimes you just have to guess, because what can you say? It looks like it's a maximum. But remember, the RMS is much less than that. So what if that's what we are referring to? But on this graph, it's on maximum voltage, so we're going to assume it's maximum power. Right. Okay, so let's get to the next question. It says, provide 2 reasons why alternating current is preferred over direct current. Easy. So this is 9.2.5. Well, the first one, we know that it can be stepped up. Can be stepped up. Through transformers. Right? Second one, that it is cheap. To generate even. And even propagate, I guess. So something cheap, guys, you can do whatever with it. Imagine direct current for longer distances would be a disaster, right? So in fact, instead of saying cheap, you can even say cost effective to try and be very diplomatic, You can say it is cost effective. It is cost. Although our government is ripping us off, making it look like this thing is expensive. Because they just want to steal. Oh, Lord. Sometimes when you have people who have no honor, like we have our politicians in this country, you just wish you were never born, hey? Yeah, because why would you be born and be represented by people like these who have no dignity whatsoever? Anyway, what can we do, man? People choose their fate anyway, so we cannot say much. They chose to be rotten. There's nothing we can do about it. Everyone was given free will by God, and He gave us all an equal amount of time and opportunity on this earth. It's up to us what we do with it. He told us that we can choose for ourselves, as long as we can live with the consequences of our choices. that guy is fine. We can judge all we want and say, yeah, if you do bad, you're gonna die. It's just psychological bullshit. A lot of people don't realize that a lot of things they wish upon others is just them treating their own frustrations. But it's not gonna happen, guys. It's not gonna happen. You see, the reality is we choose our own fate when we choose how we live the life that God gave us. He gives us everything, but we decide what we do with that. Okay? Yes, if you do bad things, sooner or later bad things are going to catch up with you, but they're not going to catch up with you because someone else wishes so. No. Is that every action has a reaction. Newton's third law taught us that, and it's real. You do good, you're likely to get good things coming your way. But there are times when you do good, but only bad results come. So what do you say under those circumstances? You will say misfortune. Again, another way of just hiding from the truth. It just shows, man, that certain actions, as good as they are, they're not carefully thought out. And therefore, a reckless action never amounts to any good, no matter how well wishing or how well meaning is the person behind it. If you're not doing the right thing, it's like seeing a person standing on the street begging for money. You know, when you have a bit of money in your pocket, you start to feel blackmailed that, look, I have enough money and I'm not going to do anything. Let me give this poor soul. Remember, guys, when you're doing that, you're destroying that individual, because that person is going to go and smoke drugs and go and cause chaos in their family. So they need to know that going to the streets and begging is not the way of living. First of all, you don't know those people. So you don't know where they come from. You don't know what is going on in their lives. You don't know what they're going to do with what you're giving them. You are just probably perpetrating a very disastrous situation here for the family, who actually is struggling to get this person under control. Just learn to keep your money in your bank, folks. If you have more money than you can ask for it, just keep it in the bank. If you don't know what to do, stop giving it around. Okay? Because we actually start trouble for other people thinking we are helping. So this is just to say, a not so well thought out plan with a clear vision, it never amounts to much. Instead, it can cause trouble. All right? Anyway, let's just do the physics here before I start talking non-stop. Question 10 reads, learners demonstrated the photocell effect by irradiating green and blue light on a photocell as shown. Remember, the plate on which the light is incident is the cathode, and it is connected to the negative end of our cell. Okay, so it is negative. Now we strip electrons, then they accelerate towards the anode. This one is the anode, so know these things. Okay. Anyway, so that's the story. So if the green light emits electrons, obviously the blue light will also do the same because it's higher energy than green. Remember the question? So I'm sure they wanted to use blue light. Can you see? There it is. There's green and blue. So probably that question that got botched, it must have been suggesting a blue light. Anyway, if the green can emit electrons, obviously the blue is higher energy than green. So definitely it will. Right, but the only difference is that the electrons here, if we use the same intensity, it means we're going to deliver the same number of photons. Now each photon empties all its energy to exactly one electron. So that means the number of electrons is not going to be affected, which means the current is not going to be affected, but the kinetic energy of those electrons is going to be much faster. All right. Anyway, so think about these things, guys, when dealing with this question. It's usually not so complex as well. says now the reading is registered on the ammeter when green light is used in the photocell above. Provide a reason for this observation. Obvious. We can just say the green light is of sufficient energy to emit electrons on the metal surface. Okay? Meaning the work function. You can say the energy of the green light, of a photon of green light. Energy of a photon of green light is greater than the work function of the element. Okay, I mean, guys, I'm giving too much, but either one of the two things that I just said could be enough. Because once you say sufficient, it means the energy of the photon from the green light is certainly greater than the work function. That's why it can emit electrons, which actually have kinetic energy, and hence we get a current. So just the first one is good enough, guys. But again, this is just another way to phrase it. Or you can give it as some whatever. So 10.2 reads, the green light is now replaced with blue light of the same intensity. Wow. And irradiated onto the photocell. What influence will this have on the following? Of course, remember, same intensity means same number of photons. That means we're going to emit the same number of electrons as the green light did. The kinetic energy of the photoelectrons, it certainly should increase. Yes. 10.2.2, it increases. Why? Because the photoelectric equation says E is equal to the work function plus the EK max of the photoelectrons. Now, the more energy, then it means this one increases. Right? Because if this guy increases, if that guy increases, that means the kinetic energy will also increase, isn't it? Yes, 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 and yes. Okay. But again, this is a correlation rather than a direct proportionality of some sort, you see. Be very careful of these things. These equations are important to understand. Okay, this one we just get 1 mark because no explanation is needed. 10.2.3 says the reading on the ammeter, again, it does not increase, it stays the same. Okay, unfortunately, we need to explain the answer. Of course, we can say the same intensity of blue light as green light means there is equal number of photons reaching the cathode. Right. You can say since one photon is equal to one photoelectron, there will be an equal number of photoelectrons emitted, then the current will be the same due to, we know that current is given by charge divided by time. So it's the amount of charge passing a point. So we can even say the number of charges passing a point per second. That's the Ampere law, isn't it? So we can say the current, if we're saying that the amount of charge is constant, this is in 1 second. So in essence, we understand that current is directly proportional to charge in 1 second per unit time, meaning per second. Usually when we calculate current, we talk about per second. Okay guys, so that's just the story there. Nothing really major, more strategy, that's all. So we can say it stays the same, and we can say the intensity means the same number of photons, then same number of photoelectrons, and then the current, explaining it using what we call the Quit equation. Anyway, that's the one, guys. So I don't have a lot, but this one. Now let's see, can we do this one? 10.3 says the wavelength of blue light is 4,5 times 10 to the minus 7 meters. Calculate the cutoff frequency or threshold frequency of the metal used in the photocell if the average speed of the emitted photoelectrons is this. Okay, cool, let's do it. We know that the energy of a photon is going to be equal to the work function of the metal plus the kinetic energy maximum of the photoelectron. So this is what we call the photoelectric equation. So we know that the energy is basically Planck's constant times the frequency, which is going to be Planck's constant times the threshold frequency plus half mv squared. Okay. We go on. Now we don't have frequency, we're given wavelength. So we know that frequency using the speed of light in a vacuum is going to be frequency times lambda. So this is h times c over lambda. Is going to be h times this. Okay. So let's move, guys. Planck's constant is 6,63 times 10 to the minus 34, right? And what is the speed of light in a vacuum? I forgot, folks. Let's go and have a look. The c is 3 times 10 to the 8, okay? All divided by the wavelength here. We're told it's 4,5 times 10 to the minus 7 equals 6,63 times 10 to the minus 34. Is that the one? Where is Planck's constant here? Is this the one? Yeah, this is the one. Okay. So times the threshold frequency, which is what we want, plus half. What is the mass of an electron? Is 9,11 times 10 to the minus 31. So what is the mass? Sorry, the velocity was 4,62 times 10 to the 5 squared. Okay. Right, so let's manipulate this nicely. But these numbers irritate me, but yeah, let's just clean it up a bit. So let's say 6,63, 6,63 times 10 to the minus 34 into 3 times 10 to the 8 divided by 4,5 times 10 to the minus 7. So this is what we get, 4,42 times 10 to the minus 19 equals 6,63. Okay, plus 0,5 into 9,11 times 10 to the minus 31 into 4,62 times 10 to the 5 squared. So this one gives us a 9,7224 times 10 to the minus 20. Okay. Now we can see that we can isolate our threshold frequency by saying this is 4. But hey. Oh yeah, it's not going to be small. Okay. Minus 19 can take 9,7224 times 10 to the minus 20. That's smaller. And then we divide this by the Planck's constant, 6,63 times 10 to the minus, what are you doing? You can say therefore our threshold frequency will be, so let's do it, 4,42 times 10 to the minus 19 minus 9,7224 times 10 to the minus 20 divided by 6,63 times 10 to the minus 34. So we get a 5,20 times 10 to the exponent 14. Remember, this is capital letter H, small letter Z. Okay. Alright guys, here there's big numbers. Mistakes can occur. Please just double check if everything is gelling. It's easy to make an error. It's just like electrostatics. It's just irritating with those big numbers and scientific notation of very small and very big numbers. Anyway guys, if this is bad, it's up to you now to correct whatever went wrong. I'm tired. So we can give a mark here and give a mark there and say the general substitution. So 1, 2, 3, 4, then say 5. But now we're getting 6 marks for the y. Anyway, there's a lot that we did. We found the Planck's constant. We found the speed of light in a vacuum. So maybe that could be the one. Yeah, anyway guys, 6 marks is in the bag if everything is correct. It's easy to make mistakes otherwise. So rather start with these sections guys so that you minimize these mistakes, because when tired and dealing with these crazy numbers in scientific notation, it can hurt. Anyway guys, that's the end of our review. I hope you've enjoyed it, and those who wrote this paper, I'm sure you can see perhaps where your challenges have been and where your weaknesses were. At the same time, my channel has always been around, and I've always given this analysis on past exam question papers. I'm sure if you've been religiously following it and not just passively doing so, but perhaps imitating and emulating what you see, you should have had it easy in these exams. But again, it takes your initiative guys and your dedication to your work to do good. Otherwise, I will see you guys next time. Goodbye.